Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're setting our sights on something so astonishing that even astronomers had to pause for a moment when they realised what they were looking at. Not a galaxy, not a cluster of galaxies, not even a particularly enthusiastic supernova. Instead, we're going to spend some time with a black hole. Now that might not sound unusual at first. After all, black holes have become the celebrities of modern astronomy. They're everywhere in documentaries, science articles and computer animations. Some sit quietly in the centres of galaxies, others collide and send ripples through space itself. A few have even been photographed, or at least photographed in the same way that taking a picture of a shadow counts as photographing the thing casting it. But the object we'll be exploring tonight belongs in a category of its own. This black hole is called J0529-4351. Not exactly a name that rolls off the tongue. It sounds less like the most powerful black hole ever discovered, and more like a droid who forgot to update its software. Yet behind that rather unassuming label lies one of the most extreme objects humanity has ever found. In fact, it shines so brightly that it outshines entire galaxies. Not stars, not solar systems, galaxies. Before we settle into that remarkable idea, I'd love to know where you're listening from tonight. What part of the world are you in right now? Is it late evening, early morning? Perhaps you're curled up beneath a blanket while rain taps softly against the window. Maybe you're listening while the rest of the house is asleep, or perhaps you're somewhere on the other side of the planet where daylight is just beginning. And what time is it for you right now? It's a fitting question for a journey that will carry us billions of years into the past. If you find these sleepy explorations relaxing, interesting, or simply a pleasant way to unwind after a long day, I'd be very grateful if you gave the video a like and perhaps subscribed as well. It helps this quiet corner of science find other curious minds who might enjoy drifting off among the stars. Now, make yourself comfortable. Settle into your favourite sleeping position. Let your shoulders relax, and together let's travel toward one of the brightest and most powerful objects ever discovered in the known universe. The story begins with a strange realization. When most people picture a black hole, they imagine darkness. It's understandable. The name itself practically demands it. Black hole. A region of space so dense that not even light can escape. If light cannot escape, then surely a black hole should be completely invisible. And in a sense, that's true. The black hole itself is dark, completely dark, utterly dark. The problem is that black holes are often terrible neighbours. They have a habit of pulling in enormous amounts of surrounding material, gas clouds, dust, occasionally stars. Anything that wanders too close can find itself trapped by the black hole's immense gravity. And that's where things become surprisingly bright. Imagine pouring water down a drain. The water doesn't instantly disappear. Instead, it swirls around the drain in a spinning spiral. Material falling toward a black hole behaves in a somewhat similar way, except instead of water, we're talking about entire clouds of gas spanning distances larger than our solar system. As this material spirals inward, it forms a structure called an accretion disk. The gas within that disk moves at extraordinary speeds, millions of kilometers per hour, faster, much faster. The particles collide with one another constantly. Friction builds, temperatures rise, the gas becomes so hot that it begins to glow. Then it glows more, then more, then more. Eventually the accretion disk becomes one of the brightest things in the universe. Ironically, the brightest black holes are bright precisely because they're consuming so much material. They're cosmic engines converting matter into radiation with astonishing efficiency. If that sounds impressive, keep that thought in mind. Because J0529-4351 isn't merely feeding, it's feasting. Astronomers estimate that this object consumes roughly the equivalent of one sun every single day. Pause for a moment and think about that. Our Sun contains approximately 330,000 times the mass of Earth. Every day, J0529-4351 adds about a solar mass worth of material to its enormous appetite. While you're sleeping tonight, it will consume another sun. By tomorrow night, another, and another, and another. If black holes had restaurant reviews, this one would permanently occupy the top position. Yet even that astonishing feeding rate doesn't fully explain why astronomers became so excited. The real surprise came when they measured its brightness. At first glance, J0529-4351 appeared to be a star-like object. That's actually how many quasars appear through telescopes. A quasar, short for quasi-stellar object, often looks like an unusually bright point of light. For decades, astronomers occasionally mistook quasars for stars because they appeared so compact. The difference is that stars are relatively nearby. Quasars are unimaginably distant, and that means their brightness is deceptive. Imagine standing on a hill at night. Far away, you notice a tiny light on the horizon. Perhaps it's a flashlight. Perhaps it's a bicycle lamp. That's a reasonable assumption because it looks small and faint. Now imagine discovering that the light wasn't nearby at all. Instead, it was thousands of kilometers away. Suddenly, you'd realize the source must be extraordinarily powerful to remain visible across such a vast distance. That's essentially what happens with quasars. They appear as tiny points, yet they're located billions of light years away. For us to see them at all, they must be producing truly ridiculous amounts of energy. J0529-4351 turned out to be one of the most extreme examples ever discovered. The numbers involved are so large that they begin to lose their meaning, and that's one of the challenges we'll face throughout this journey. Human beings are reasonably good at understanding small numbers. We can picture 10 apples, 100 people, 1,000 books. Once we move into astronomical territory, however, things become more difficult. Millions become abstract, billions become fuzzy, trillions become almost impossible to visualize. The universe, unfortunately, has no sympathy for this limitation. It keeps producing objects that casually exceed our imagination. J0529-4351 is one of those objects. The light reaching Earth from this quasar began its journey more than 12 billion years ago. That means we're not seeing it as it exists today, we're seeing it as it existed when the universe was much younger. In a very real sense, every telescope is a time machine. Light travels at a finite speed, fast certainly, incredibly fast. About 300,000 kilometers every second. Yet space is so vast that even light requires time to cross it. The sunlight warming Earth today left the sun about 8 minutes ago. The light from our neighbouring galaxy, Andromeda, began its journey roughly 2.5 million years ago. The light from J0529-4351 started travelling toward us before Earth even existed, before the dinosaurs, before the formation of our solar system, before any human would ever look up and wonder what the stars were. That ancient light crossed billions of years of cosmic history before eventually entering modern telescopes. And when astronomers analysed it carefully, they realised something extraordinary. They were looking at what may be the most luminous known quasar in the universe. Its brightness exceeds hundreds of trillions of suns combined. Take a moment with that number, hundreds of trillions. Our sun produces more energy every second than humanity could use in millions of years. Yet J0529-4351 effectively combines the output of hundreds of trillions of suns. Trying to imagine such brightness is a bit like trying to imagine the total number of grains of sand on every beach you've ever visited, while simultaneously counting every raindrop in a thunderstorm. Eventually the mind politely declines and changes the subject. Fortunately, astronomy has developed methods for handling these absurd scales. Astronomers don't simply stare at an object and guess its brightness. They measure wavelengths. They analyse spectra. They calculate distances. They compare observations from different instruments. Piece by piece, the true nature of an object emerges. Sometimes those investigations reveal something ordinary, a star, a galaxy, a cloud of gas. Other times they reveal something capable of rewriting records. J0529-4351 belongs firmly in the second category. What's particularly fascinating is that this object remained hidden in plain sight for years. The sky's enormous. There are billions of objects visible to modern surveys. Separating one unusual point of light from countless others is a little like searching for a specific grain of sand on a beach the size of a continent. Astronomers rely heavily on automated surveys and sophisticated software. Even then, remarkable discoveries can remain unnoticed until someone looks more closely. That's exactly what happened here. When researchers revisited existing observations with improved techniques, they realized they were not looking at an ordinary object. The brightness was too extreme. The characteristics were too unusual. Further investigation revealed a monster, a genuine cosmic heavyweight, one of the fastest growing black holes ever identified, and perhaps the most energetically powerful known object of its kind. There's something wonderfully humbling about discoveries like this. For thousands of years, humanity studied the sky using only our eyes. Then came telescopes, then photography, then radio astronomy, then space observatories. Each new generation of technology revealed a larger universe than anyone expected. Every time we think we've found the limits of cosmic scale, the universe quietly presents another surprise, a larger star, a more massive galaxy, a more distant object, a black hole that apparently missed every lesson about moderation. J0529-4351 is a reminder that nature has no obligation to remain within the boundaries of our intuition. The cosmos routinely creates things that seem exaggerated even by science fiction standards, and yet, despite its extraordinary power, this object obeys the same laws of physics that govern everything else, the same gravity that causes an apple to fall, the same electromagnetism that powers a light bulb, the same atoms found in your body. Somewhere in the distant universe, those familiar laws combined in exactly the right way to create one of the brightest objects ever observed. That realization brings us to an interesting question. If J0529-4351 is so bright, so massive and so powerful, what exactly are we looking at? Is it merely a giant black hole? A special kind of black hole? Something else entirely? A curious thing happens whenever people hear the words black hole. Almost immediately the imagination takes over. Some picture a giant vacuum cleaner drifting through space, sucking up everything in its path. Others imagine a dark cosmic tunnel leading somewhere mysterious. A few imagine an enormous mouth endlessly swallowing stars, planets, and anything unfortunate enough to wander nearby. Hollywood has certainly encouraged these images over the years. To be fair, black holes are strange enough that they hardly need any extra help from science fiction. Yet before we continue our journey toward J0529-4351, the most powerful black hole ever discovered, it's worth slowing down for a moment and asking a surprisingly simple question. What is a black hole really? Because despite their reputation, black holes are often misunderstood. In fact, one of the first things that surprises people is that black holes are not actually cosmic vacuum cleaners. If our sun suddenly became a black hole tomorrow, Earth would not be pulled inward and swallowed. Now there would be several other problems with that situation. The sudden disappearance of sunlight would certainly make for a difficult morning, but gravitationally speaking, Earth would continue orbiting exactly where it is. The reason is straightforward. Gravity depends on mass. If the sun somehow became a black hole while keeping the same mass, its gravitational pull on Earth would remain unchanged. We would still orbit it. The difference would simply be that the mass would occupy a much smaller region of space. And that brings us closer to the true nature of a black hole. At its heart, a black hole is not really an object in the traditional sense. It's a region of space where gravity becomes so intense that nothing can escape once it crosses a certain boundary. Not light, not particles, not information, at least as far as our current understanding allows. Nothing. That boundary is called the event horizon. The name sounds dramatic because it is dramatic. The event horizon marks the point beyond which escape becomes impossible. Cross it, and every possible path leads inward. Imagine standing beside a waterfall. Far upstream, you can swim wherever you like. The current might be strong, but you still have options. Closer to the edge, the current becomes faster. Eventually you reach a point where even the strongest swimmer could no longer fight against the flow. Beyond that point, the waterfall determines your future. The event horizon is somewhat similar. Outside it, movement in many directions remains possible. Inside it, every possible future points toward the center. No amount of effort can reverse the journey. Gravity wins every time. That description naturally raises another question. How can gravity become that strong? The answer begins with stars. For most of their lives, stars perform an extraordinary balancing act. Gravity constantly pulls matter inward. Meanwhile, nuclear fusion deep within the core produces energy that pushes outward. These opposing forces maintain a delicate equilibrium. For billions of years, stars exist in this balance. Gravity squeezes, fusion pushes back. Neither side fully wins. Our own sun is currently enjoying this arrangement. Every second it converts millions of tons of hydrogen into helium. The process releases immense energy. That energy prevents the sun from collapsing under its own weight. But no star possesses an infinite fuel supply. Eventually the fuel runs low. The exact outcome depends largely on mass. Smaller stars end their lives relatively peacefully. Larger stars experience far more dramatic finales. When a massive star exhausts its fuel, gravity suddenly finds itself facing much less resistance. The core begins collapsing. Matter falls inward at extraordinary speeds. Temperatures soar, pressures rise. Then comes one of the most violent events in the universe, a supernova. For a brief period, a dying star can outshine entire galaxies. The explosion blasts outer layers into space while the core continues collapsing. If enough mass remains, not even the pressure generated by tightly packed particles can stop gravity's advance. The collapse continues, the core shrinks and shrinks and shrinks. Eventually an object forms whose escape velocity exceeds the speed of light itself. At that moment, a black hole is born. The concept sounds almost absurd, something so compact that light cannot escape. Yet nature appears perfectly comfortable creating such objects. In fact, the universe seems rather fond of them. Black holes exist throughout the cosmos. Some form from collapsing stars, others grow gradually over billions of years. A few become truly enormous. The black holes found at the centers of galaxies belong to this last category. These are called supermassive black holes, and they make stellar black holes look surprisingly modest. A typical stellar black hole might contain 5 or 10 times the Sun's mass, perhaps 50, maybe even a few hundred. A supermassive black hole can contain millions or billions of solar masses. The black hole at the center of the Milky Way, known as Sagittarius, a star, contains roughly 4 million times the mass of the Sun. That sounds enormous. And it is. Yet as impressive as Sagittarius, a star, may be, it would eventually look rather small compared with the object we're building toward. Because J0529-4351 belongs to a class of black holes so extreme that even astronomers accustomed to large numbers had to double-check their calculations. We'll get there soon enough. For now, let's stay with the fundamentals. One of the strangest things about black holes is that nobody has ever directly seen one. At least not in the ordinary sense. That statement might sound surprising given all the headlines you've probably encountered. After all, didn't scientists photograph a black hole? Yes. And no. What they photographed was the region surrounding a black hole. Specifically, they captured the shadow cast against glowing material nearby. It's a bit like photographing a silhouette. You aren't seeing the object itself, you're seeing the effect it has on light around it. The famous image of M87 star revealed a glowing ring surrounding a dark centre. That dark centre marked the shadow of the event horizon. Even in one of humanity's greatest astronomical achievements, the black hole itself remained hidden. In a sense, invisibility is part of its defining characteristic. This invisibility creates an interesting challenge. How do astronomers find black holes at all? The answer involves watching what happens around them. Gravity leaves fingerprints. Even when an object cannot be seen directly, its gravitational influence can reveal its presence. Suppose you observe a star moving in a tight orbit around an apparently empty region of space. Something must be pulling on it. If calculations indicate millions of solar masses squeezed into a tiny volume, a black hole becomes the most likely explanation. The same principle applies on larger scales. Astronomers watch stars orbit galactic centers. They observe gas clouds accelerating. They detect powerful jets of radiation. They measure gravitational effects. Piece by piece, black holes reveal themselves through their influence on the surrounding universe. It's rather like tracking an invisible animal through footprints in fresh snow. You never see the creature directly. Yet the evidence becomes overwhelming. Interestingly, black holes are not merely destroyers. Popular culture often portrays them as cosmic monsters, whose only purpose is consuming things. Reality is more nuanced. Many galaxies appear to depend on their central black holes. Over the past few decades, astronomers have discovered something remarkable. The size of a galaxy's central black hole often correlates with the size of the galaxy itself. Larger galaxies tend to host larger black holes. Smaller galaxies host smaller ones. The relationship is so consistent that many researchers believe black holes and galaxies evolve together. In other words, black holes may help shape entire galaxies. That's a remarkable shift in perspective. Instead of being cosmic accidents lurking in dark corners, black holes may be key architects of galactic evolution. The Milky Way itself likely owes part of its history to the influence of Sagittarius A star. For decades, scientists assumed galaxies formed first and black holes appeared later. Today, the relationship seems far more complicated. It's possible that black holes played important roles from the very beginning. Perhaps they even helped organize some of the largest structures in the universe. That possibility becomes especially important when we consider objects like J0529-4351. Because one of the greatest mysteries in modern astronomy is how such enormous black holes formed so quickly. The universe, after all, is old. About 13.8 billion years old. That sounds like plenty of time, yet many gigantic black holes appear surprisingly early in cosmic history. They reached extraordinary masses when the universe was still relatively young. It's a little like finding a fully grown redwood tree in a field that was planted only a few years ago. Something doesn't quite add up. Either these black holes grew much faster than expected, or our understanding of their formation remains incomplete. Astronomers are actively investigating both possibilities. Another misconception worth addressing involves what happens if something falls into a black hole. Science fiction often depicts dramatic stretching, twisting, and destruction. Interestingly, this part contains some truth. The phenomenon is sometimes called spaghettification. Yes, that is the actual term. Scientists occasionally display a delightful willingness to abandon serious naming conventions. The idea is simple. Gravity becomes stronger as you approach a massive object. Near a black hole, the difference in gravitational pull between your feet and your head can become enormous. Your feet experience stronger gravity than your head. The result is stretching. Potentially a lot of stretching, eventually far more stretching than any human would prefer. For smaller black holes, this process occurs before crossing the event horizon. For truly gigantic black holes, however, the event horizon can be surprisingly gentle, at least initially. A traveller crossing it might not notice anything unusual immediately. No dramatic boundary, no flashing sign, no cosmic announcement. The event horizon itself is not a physical surface, it's a mathematical boundary. You simply cross it. The problem comes later when gravity continues increasing during the inward journey. Fortunately for all involved, this remains a purely theoretical concern. No human has ever approached a black hole closely enough to test the experience firsthand, and given current technology, nobody will be volunteering anytime soon. Still, these thought experiments help illustrate just how strange black holes truly are. They occupy a fascinating intersection between gravity, space, time, and the limits of our understanding. In fact, black holes helped produce some of the greatest scientific breakthroughs of the last century. When physicists tried to understand them, they discovered connections between gravity and thermodynamics, between quantum mechanics and information theory, between the very large and the very small. Black holes became laboratories for fundamental physics. They forced scientists to confront questions that remain unanswered today. What happens to information inside a black hole? Can gravity be unified with quantum mechanics? What occurs at the very centre? The truth is that we still don't know, and that uncertainty makes black holes even more fascinating. Every time astronomers uncover a new extreme example, they gain another opportunity to test their theories, another chance to learn something unexpected, another chance to discover that the universe is stranger than anticipated. Which brings us back toward J0529-4351. Because now we have the foundation. We understand that black holes form when gravity overwhelms every opposing force. We understand that some become supermassive. We understand that material falling toward them can generate tremendous amounts of energy. And we understand that black holes are often discovered through the effects they produce, rather than through direct observation. Something rather interesting happens in astronomy from time to time. Scientists spend years building powerful telescopes, designing sophisticated instruments, and creating elaborate theories about the universe. Then, after all that preparation, one of the biggest discoveries arrives because someone looks at existing data and notices that something seems a little odd. Not wrong, not impossible, just odd. The story of J0529-4351 begins with exactly that kind of moment, and in a way that makes the discovery even more fascinating. Because the brightest known quasar in the universe wasn't hiding behind some distant galaxy that required a revolutionary telescope to uncover. It wasn't buried inside a secret corner of space that nobody had ever examined before. Instead, it appears to have been sitting in astronomical data for years, the cosmic equivalent of misplacing your car keys only to discover they were on the kitchen table the entire time. Of course, finding a black hole billions of light years away is slightly more complicated than locating misplaced keys, but the principle is surprisingly similar. The challenge wasn't that the object was invisible. The challenge was recognizing what it actually was. To understand how this happened, imagine standing in a crowded football stadium filled with 80,000 people. Now imagine somebody tells you that one person in the crowd is secretly the richest individual on Earth. Finding that person wouldn't be easy. Not because they're hidden. Not because they're disguised. Simply because there are so many people to examine. Modern astronomy faces a similar problem. The night sky contains an almost absurd number of objects. Stars, galaxies, nebulae, quasars, asteroids, variable stars, binary systems, white dwarfs, supernova remnants, and countless other phenomena. Every major sky survey collects information on millions or even billions of objects. Each one appears as a point of light accompanied by measurements, colours, brightness levels, and spectral data. Somewhere within those enormous databases may be discoveries nobody has recognised yet. In fact, astronomers sometimes joke that there are probably groundbreaking discoveries already sitting on hard drives waiting for someone to notice them. J0529-4351 turned out to be one of those cases. The object had been observed previously. Light from it had already entered telescopes. Detectors had already recorded its presence, yet its true nature remained overlooked. The reason comes down to one of astronomy's oldest challenges. Distance can be deceptive, very deceptive. Let's return for a moment to a simple thought experiment. Suppose you're standing outside at night and notice a faint light in the distance. At first glance, you might assume it's something relatively small, perhaps a porch light, maybe a bicycle lamp. The object appears faint, so your brain naturally assumes it isn't particularly powerful. But what if that same faint light were actually hundreds of kilometers away? Suddenly the situation changes completely. The light source would need to be enormously bright to remain visible from such a distance. Astronomers constantly face this problem. When observing distant objects, brightness alone doesn't tell the whole story. An object may appear faint because it's weak, or it may appear faint because it's unimaginably far away. Determining which explanation is correct requires careful investigation. This becomes especially important when studying quasars. Quasars are among the most luminous objects in existence. They are powered by supermassive black holes actively feeding on surrounding matter. As gas spirals inward, enormous amounts of energy are released. The result is a brilliant beacon visible across billions of light years. In many cases, a quasar can outshine the entire galaxy surrounding it. Imagine lighting a single candle so bright that it becomes more visible than an entire city. That's roughly the level of absurdity we're dealing with. Yet despite their incredible luminosity, quasars often appear deceptively ordinary in surveys. Through many telescopes they resemble stars, tiny points of light, nothing obviously dramatic, certainly not objects powered by black holes containing billions of solar masses. As a result, astronomers have spent decades developing methods to distinguish quasars from stars. Color measurements help, spectral analysis helps. Statistical techniques help. Even so, mistakes happen. Some quasars are classified incorrectly. Some stars mimic quasar characteristics. Some objects fall into confusing categories, and occasionally a truly extraordinary object slips through the cracks. J0529-4351 appears to have done exactly that. For years, it was essentially mistaken for something far less remarkable. Not because astronomers were careless, far from it. The reality is that modern sky surveys generate astonishing amounts of information. Consider what happens during a major astronomical survey. A telescope systematically scans huge portions of the sky. Every image contains thousands or millions of sources. Software catalogues each object. Measurements are recorded. Databases expand. Researchers search for specific targets. The process is efficient, necessary even. Without automation, modern astronomy would grind to a halt. Yet automation has limitations. Computers excel at following predefined rules. They are less effective at recognizing unexpected extremes. Sometimes an object falls just outside the assumptions built into the system. When that happens, remarkable discoveries can remain hidden in plain sight. Around the world, astronomers continuously revisit older observations using improved methods. New software, better calibration, more complete datasets, fresh perspectives. This process often produces surprises. J0529-4351 emerged from exactly this kind of re-examination. Researchers began studying objects that displayed unusual characteristics. Some appeared brighter than expected. Others possessed peculiar spectral signatures. The goal was straightforward: determine whether these objects were ordinary stars, quasars, or something else entirely. As observations accumulated, J0529-4351 began attracting attention. The numbers simply didn't fit comfortably within expectations. Its brightness seemed extraordinary. Its distance appeared immense. Its properties suggested an object operating on a scale rarely encountered. Naturally, astronomers became skeptical. Scientific skepticism is healthy. In fact, it's essential. Whenever researchers encounter something seemingly record-breaking, the first assumption is usually that a mistake has occurred somewhere. Perhaps the instrument calibration is wrong. Perhaps the distance estimate is incorrect. Perhaps another object is contaminating the measurements. Perhaps there's a software issue. Perhaps there's a misunderstanding. Astronomers would much rather eliminate every possible error before announcing a discovery. Nobody wants to publish a paper claiming they've found the brightest quasar ever observed only to discover later that they accidentally measured a nearby street lamp. So the investigation continued. Additional observations were obtained, measurements were checked, calculations were repeated, distances were refined, spectra were analysed in detail. And with each new piece of evidence, the conclusion became harder to avoid. The object really was that bright, really was that distant, really was that extreme. At some point, excitement began replacing skepticism. Because if the measurements were correct, then researchers weren't simply looking at another quasar. They were looking at one of the most luminous known objects in the universe. One of the remarkable aspects of astronomy is that discovering an object often means discovering its past. When astronomers observed J0529-4351, they weren't seeing it in the present. They were seeing ancient light. The photons entering telescopes had travelled for more than 12 billion years. Think about that for a moment. The light began its journey long before Earth formed, long before our Sun ignited, long before the Milky Way reached its current appearance. During all that time, the universe expanded, galaxies evolved, stars were born and died, entire cosmic eras unfolded. Meanwhile, those photons continued moving through space, year after year, million year after million year, billion year after billion year. Eventually they reached Earth, then a telescope, then a detector, then a scientist's computer screen. It's difficult not to find something deeply satisfying about that process. A signal created billions of years ago arriving precisely when humanity developed the technology necessary to understand it. And what a signal it was. When the final calculations were completed, the estimated luminosity reached astonishing levels. J0529-4351 was producing energy equivalent to hundreds of trillions of suns. The number sounds almost fictional. Even professional astronomers sometimes struggle to develop intuition for such scales. After all, our Sun is hardly a modest object. Every second it releases more energy than humanity could generate in countless years. Its light powers Earth's climate, drives photosynthesis, supports nearly every ecosystem on our planet. Now multiply that by hundreds of trillions. The resulting figure becomes so large that ordinary language begins surrendering. This is where comparisons become useful. Suppose every star in the Milky Way suddenly turned on at once. Not just visible stars, every star. Astronomers estimate our galaxy contains roughly 100 billion stars. That's a tremendous number, yet J0529-4351 rivals or exceeds the combined luminosity of entire galaxies. A single black hole-powered system competing with hundreds of billions of stars. The scale is difficult to overstate. Even more remarkable was the realization that the brightness wasn't coming directly from the black hole itself. Remember, black holes are dark. The luminosity originated from matter spiraling inward, an accretion disk operating with extraordinary efficiency. Gas falling toward the black hole released immense amounts of energy before crossing the event horizon. In essence, astronomers had discovered the brightest known example of a cosmic feeding frenzy. A black hole consuming matter at a rate so extreme that it became visible across much of the observable universe. Naturally, this raised new questions, many questions. How massive was the black hole? How quickly was it growing? How could something become so enormous so early in cosmic history? Had astronomers discovered a rare exception? Or were there other giants still waiting to be found? The excitement surrounding J0529-4351 wasn't merely about setting records. Astronomers don't spend decades building observatories simply to create larger numbers. The real value lies in what extreme objects reveal about the universe. Every record-breaking discovery tests existing theories. Every outlier challenges assumptions. Every extreme case forces researchers to ask whether current models are complete. Imagine discovering a tree twice as tall as any tree previously known. You wouldn't simply admire its height. You would wonder how it grew, what conditions allowed it. Why is it different? Could there be others? J0529-4351 presented a similar puzzle. If such a massive luminous black hole existed when the universe was relatively young, perhaps black hole growth occurs more rapidly than expected, or perhaps some special mechanism was involved, or perhaps astronomers were only beginning to glimpse the upper limits of what nature could create. The discovery opened doors rather than closing them, and that may be the most exciting aspect of science. Every answer tends to generate additional questions. Astronomy especially seems to operate this way. Find a larger galaxy. Why is it so large? Find a more distant quasar. How did it form? Find the brightest known black hole. How is that even possible? J0529-4351 quickly transformed from a curious observation into a major scientific mystery. Researchers around the world began examining its properties. Theoretical models were revisited. Comparisons were made with other quasars. Data continued accumulating. The object had gone from being overlooked to becoming one of the most fascinating black holes ever discovered. There's a peculiar challenge that appears whenever astronomers try to describe something truly enormous. At first, the numbers sound impressive, then they become difficult to imagine. Eventually they become so large that the human brain quietly stops participating in the conversation. J0529-4351 belongs firmly in that final category. By now, we know that astronomers discovered an object brighter than any known quasar ever observed. We know its light travelled for more than 12 billion years before reaching Earth. We know it is powered by a supermassive black hole feeding at an astonishing rate. But none of those facts fully capture what we're dealing with. To appreciate J0529-4351 properly, we need to stop thinking about it as merely another black hole. Because if you heard the phrase black hole, you might naturally picture darkness. You might imagine an invisible region of space silently pulling things inward. You probably wouldn't imagine one of the brightest objects in the entire observable universe. And yet that's exactly what J0529-4351 is. In fact, if you could somehow place it at the centre of our Milky Way and observe it safely from a great distance, the night sky would become almost unrecognisable. The object would dominate everything. Stars would fade into relative insignificance. Entire regions of the galaxy would seem dim by comparison. A black hole would become the brightest thing around, which sounds completely backwards. After all, black holes aren't supposed to shine, at least not directly. The black hole itself remains dark. The event horizon emits no light, no glow, no sparkle, no cosmic spotlight. Instead, the brilliance comes from what surrounds it. And what surrounds J0529-4351 happens to be one of the most energetic environments known to science. To understand why, imagine standing beside a river. Water flows steadily downstream. The movement appears smooth from a distance, but look more closely near rocks or narrow passages and you notice turbulence, whirlpools, collisions, friction, energy being transferred from one place to another. Now replace the river with an immense cloud of gas spanning distances larger than our solar system. Replace the gentle current with material moving at significant fractions of the speed of light. Replace the rocks with a black hole containing tens of billions of solar masses. Suddenly the situation becomes much more dramatic. Material falling toward J0529-4351 doesn't simply disappear. It spirals inward, faster and faster, round and round, again and again. As it does so, particles collide constantly. Atoms smash into one another, gas becomes compressed, temperatures rise, energy is released. The result is an enormous accretion disk surrounding the black hole, and this disk is where the real story begins. Because accretion disks are among the most efficient engines in the universe, that statement deserves a moment of attention. Human civilization has spent centuries developing increasingly sophisticated ways to generate energy. We burn wood, coal, oil, natural gas. We split atoms. We harness sunlight. We build wind turbines. Every method converts matter or energy from one form into another. Yet all of them are remarkably inefficient compared with matter falling into a black hole. Consider ordinary combustion. When you burn gasoline, only a tiny fraction of the fuel's mass becomes usable energy. Nuclear fusion performs much better. That's how stars shine. The sun converts mass into energy with impressive efficiency. Even so, accretion disks around black holes can outperform stars dramatically. Matter spiraling toward a black hole can convert a significant portion of its mass into radiation before crossing the event horizon. In simple terms, black holes can extract enormous amounts of energy from infalling material. They're not bright despite being black holes. They're bright because they're black holes actively feeding. And nobody appears to be feeding more aggressively than J0529-4351. Researchers estimate that this giant consumes roughly 1 solar mass every day. That figure is so extreme it's worth examining carefully. Our Sun contains about 2 nonillion kilograms of material. That's a 2 followed by 30 zeros. Writing the number takes less effort than understanding it. Yet every day, J0529-4351 effectively adds about that much mass to its cosmic diet. Imagine placing the Sun on a conveyor belt leading toward a black hole. Every 24 hours another sun arrives, then another, day after day, year after year, for billions of years. The scale becomes almost absurd. Yet somehow the universe appears perfectly willing to sustain such behaviour. The consequence is extraordinary luminosity. As matter spirals inward, enormous amounts of energy emerge across the electromagnetic spectrum. Visible light, ultraviolet radiation, X-rays, other wavelengths. The accretion disk effectively becomes a gigantic cosmic furnace. Temperatures reach levels difficult to comprehend. In some regions, gas becomes hotter than the surface of most stars, much hotter. The resulting radiation streams outward across intergalactic distances. Some of those photons eventually begin journeys lasting billions of years. A tiny fraction ultimately reaches Earth. And even after crossing such unimaginable distances, the object remains visible. That fact alone tells us something remarkable. Light weakens with distance. Anyone who has ever used a flashlight understands this intuitively. Move farther away and the beam appears dimmer. Keep moving away and eventually it disappears. Now imagine an object remaining detectable across billions of light years. The source must be extraordinarily luminous. There is simply no alternative. In the case of J0529-4351, the numbers become almost unbelievable. Its luminosity exceeds hundreds of trillions of suns, not hundreds, not thousands, not millions, hundreds of trillions. At this point, analogies become essential because ordinary numbers lose their usefulness. Suppose every star in the Milky Way suddenly increased its brightness. Then imagine combining the light from roughly 100 billion stars. Now, imagine an object capable of rivaling that output despite occupying a region vastly smaller than an entire galaxy. That's essentially what astronomers discovered. A single black hole-powered system, competing with the combined light of hundreds of billions of stars. The contrast is astonishing. Galaxies are enormous. The Milky Way spans roughly 100,000 light-years. Its stars occupy an immense volume of space. J0529-4351 generates comparable luminosity from a much more concentrated region surrounding one central black hole, It's like comparing the illumination from an entire continent to a single incredibly powerful lighthouse. And that raises an interesting question. If the black hole itself is dark, why doesn't all that surrounding light simply fall inward and disappear? The answer involves geometry and motion. The accretion disk isn't sitting still. Material constantly moves through it. Gas spirals inward while radiation escapes outward. The system functions almost like a gigantic traffic circle. Matter enters, energy emerges, material gradually moves closer to the event horizon. Some eventually crosses the boundary. Meanwhile, photons generated during the process travel outward into space. Many escape entirely. Those escaping photons are what make quasars visible across cosmic distances. Without them, black holes would remain nearly impossible to detect. With them, objects like J0529-4351 become beacons visible across much of the observable universe. The term beacon turns out to be surprisingly appropriate. For ancient sailors, lighthouses marked dangerous coastlines. Their light travelled across dark oceans, providing guidance from enormous distances. Quasars perform a somewhat similar role for astronomers. Because they are so bright, they can be observed from extraordinary distances. Some of the earlier studies of the distant universe relied heavily on quasars. They act like cosmic backlights, illuminating material between galaxies. As their light travels toward Earth, it passes through enormous regions of intergalactic space. Gas clouds absorb specific wavelengths. Astronomers analyze those absorption patterns to learn about structures located billions of light years away. In other words, quasars don't merely reveal themselves, they help reveal everything between us and them. The brighter the quasar, the more useful it becomes, and J0529-4351 happens to be exceptionally useful. Its incredible luminosity allows researchers to probe distant regions of the cosmos with remarkable precision. Yet perhaps the most astonishing aspect of this object isn't its brightness. It's the fact that the brightness appears sustainable. A supernova can briefly outshine a galaxy, but supernovae fade. They are temporary explosions. Their brilliance lasts weeks or months. Quasars operate differently. As long as material continues falling inward, energy production continues. The engine remains active. J0529-4351 isn't experiencing a short-lived burst. It's running a long-term power plant fueled by gravity itself. That distinction matters, because sustaining such luminosity requires an enormous supply of matter. Gas must continue reaching the accretion disk. Material must continue spiraling inward. The black hole must continue feeding. Somehow, over immense spans of time, nature has managed to keep this process going. It's rather like discovering the largest campfire ever seen, and then learning it has been burning continuously for ages. You immediately begin wondering where all the fuel comes from. Astronomers wonder exactly the same thing. Every measurement of J0529-4351 raises new questions about its environment. What kind of galaxy hosts such an object? How much gas surrounds it? How did so much material reach the central black hole? What conditions allowed this feeding frenzy to persist? The answers remain active areas of research. Because despite all the observations collected so far, J0529-4351 continues to challenge existing models. One particularly striking realization emerges when comparing this object with our own galactic center. At the heart of the Milky Way lies Sagittarius, a star. It's a genuine supermassive black hole. It contains millions of solar masses, yet compared with J0529-4351, Sagittarius A star appears remarkably quiet, almost sleepy. If black holes were restaurants, Sagittarius A star might resemble a quiet neighborhood cafe, serving a few customers each day. J0529-4351 would resemble a city-sized buffet operating at maximum capacity 24 hours a day for billions of years. The difference in feeding rate is enormous. The difference in energy output is equally dramatic. This comparison helps illustrate an important point. Not all black holes behave the same way. Mass matters, environment matters, available fuel matters. Some black holes spend long periods dormant. Others become active for limited intervals. A rare few transform into quasars, and among quasars, an even rarer handful achieve truly extraordinary luminosities. J0529-4351 appears to sit near the top of that hierarchy, a record holder, a cosmic extreme. Several years ago, astronomers began realizing that J0529-4351 wasn't merely another exceptionally bright quasar. It wasn't simply another supermassive black hole sitting at the center of a distant galaxy. It wasn't even just one of the largest known black holes. The more measurements researchers collected, the more extraordinary the object became. Its brightness was astonishing. Its distance was remarkable. Its mass was difficult to comprehend. Yet one particular detail continued attracting attention. J0529-4351 appeared to be eating at a rate unlike anything astronomers had ever seen before. And when scientists talk about a black hole eating, they're not using a metaphor just for dramatic effect. A black hole grows by consuming matter. Gas falls inward. Dust follows. Stars can occasionally be torn apart. Entire clouds of material spiral toward the center. Every bit of that matter adds mass to the black hole. Over time, the object becomes larger. The process sounds simple enough. The challenge comes when we start measuring how much material is actually involved. Because J0529-4351 isn't merely feeding, it's conducting one of the largest known consumption events in the universe. To appreciate the scale involved, let's begin somewhere familiar. Imagine a large whale. A blue whale can consume several tons of food each day. That's an impressive appetite by Earth standards. Now imagine scaling upward. A herd of elephants, a city, an entire country. At every step the numbers become larger, yet eventually all earthly comparisons fail because we're dealing with a black hole whose daily diet is measured in stars. Not pieces of stars, entire stars worth of mass. Researchers estimate that J0529-4351 accumulates roughly one solar mass every day, one sun every 24 hours. It's difficult to overstate how extreme that figure really is. The Sun contains approximately 99.8% of all the mass in our solar system. Everything else combined, every planet, moon, asteroid, comet, grain of dust, and wandering rock accounts for only a tiny fraction of what resides inside the Sun. Now, imagine adding that amount of material to a black hole every single day. Tomorrow, another sun arrives. The day after that, another, then another, then another, month after month, year after year, century after century. The process continues, and that's precisely what makes J0529-4351 so extraordinary. The object isn't merely massive, it's growing rapidly, in cosmic terms, extraordinarily rapidly. Most supermassive black holes appear relatively restrained compared with this giant. They feed intermittently. Their activity rises and falls. They spend periods of relative quiet. Some remain nearly dormant for millions of years. J0529-4351 appears to have skipped those lessons entirely. If black holes attended some kind of imaginary cosmic dining etiquette school, this one clearly missed graduation day. It behaves more like an all-you-can-eat buffet discovering an unlimited supply of food. The obvious question becomes, how is this even possible? After all, space is mostly empty. The universe contains enormous distances between objects. Stars rarely collide. Galaxies are vast. Where does all the fuel come from? The answer lies in the environment surrounding the black hole. J0529-4351 exists within a galaxy rich in gas. And gas is exactly what a growing black hole wants. Unlike stars, gas clouds can be stretched, compressed, and redirected relatively easily by gravity. When enough gas begins moving toward a galactic center, it can form a gigantic accretion disk around the central black hole. The disk becomes a kind of cosmic reservoir. Material slowly spirals inward. Some moves faster, some moves slower. The entire structure rotates while gradually feeding the monster at its center. Imagine a gigantic whirlpool in an ocean. Water doesn't immediately disappear into the middle. Instead, it circles repeatedly while inching inward. Gas surrounding J0529-4351 behaves similarly. The difference is that the whirlpool spans distances so large they challenge human imagination, and the central drain happens to be one of the largest black holes ever discovered. What's particularly remarkable is that black holes cannot consume unlimited amounts of matter arbitrarily fast. There are limits. Nature imposes rules. One of the most important is called the Eddington limit. The concept is surprisingly elegant. As matter falls toward a black hole, radiation is produced. Lots of radiation. That radiation pushes outward. Meanwhile, gravity pulls inward. Eventually, these forces begin competing. Too much incoming material produces enormous amounts of radiation. The radiation itself can start pushing gas away. It's almost like the black hole's own brightness begins fighting against its appetite. Astronomers long suspected that this balance should regulate black hole growth. In simple terms, there ought to be a practical speed limit. A black hole shouldn't be able to grow infinitely fast because its own energy output creates resistance. And yet J0529-4351 appears to be operating very close to that limit. Perhaps astonishingly close. The object is feeding at a rate near what theory predicts should be the maximum sustainable level. It's effectively running one of the most powerful gravitational engines nature allows. This realization makes the system even more impressive. We're not observing a black hole lazily gathering material over billions of years. We're observing an object operating near full capacity, like a power plant pushed close to maximum output, like an engine running at the edge of its design limits, like a furnace consuming fuel almost as rapidly as physics permits. The luminosity we discussed earlier suddenly makes more sense. The incredible brightness isn't an accident, it's a consequence of the feeding process itself. More fuel means more energy. More energy means more light. More light means greater luminosity. J0529-4351 shines so brilliantly because it is consuming matter at a staggering pace. The two characteristics are inseparable. One produces the other. And this brings us to another astonishing number. The black hole powering J0529-4351 is estimated to contain around 17 billion times the mass of the Sun. 17 billion. Let's pause there for a moment. Our Sun feels large because it dominates our solar system. Jupiter, the largest planet, contains only about 1,000th of the Sun's mass. The Sun itself contains enough material to fit roughly 1.3 million Earths inside its volume. Now multiply that mass by 17 billion. The resulting object becomes almost impossible to visualize. In fact, if numbers were people, 17 billion would require more humans than currently exist on Earth. Astronomers encounter figures like this regularly, which perhaps explains why they often develop a calm demeanor. After spending years dealing with billions of solar masses and trillions of stars, ordinary numbers probably seem wonderfully manageable. Yet even among supermassive black holes, 17 billion solar masses commands respect. The Milky Way's central black hole contains roughly 4 million solar masses. That's enormous. It dominates our galactic center. It influences countless stars. It shapes the dynamics of the region around it. But compared with J0529-4351, Sagittarius A star begins looking surprisingly modest. Let's perform a thought experiment. Suppose you place Sagittarius A star on one side of a scale, then place J0529-4351 on the other. You would need thousands upon thousands of Milky Way central black holes to balance the comparison. The difference is that dramatic. And despite already being enormous, J0529-4351 continues growing. That's perhaps the most astonishing aspect of all. We're not looking at a finished object. We're looking at an object actively gaining mass. Every day adds more material. Every year increases the total. Every century makes the giant slightly larger. Granted, cosmic timescales tend to make centuries seem rather insignificant. The universe generally thinks in millions and billions of years. Still, the principle remains. The black hole is growing before our eyes, even if the changes occur too slowly for direct observation. The situation becomes even stranger when we remember distance. The light reaching Earth today left the quasar more than 12 billion years ago. We're seeing the object in its younger days, a younger version already containing 17 billion solar masses, already consuming roughly 1 sun per day, already producing extraordinary luminosity. This immediately creates a mystery. How did it get so large so quickly? The universe itself was much younger when the observed light departed. There had been less time available for growth, and yet somehow this object reached a mass rivaling the largest known black holes. Astronomers spend considerable time wrestling with that puzzle. Current models explain much, but J0529-4351 pushes those models hard. The existence of such giants suggests that under the right conditions, black hole growth can proceed with extraordinary efficiency. Perhaps giant gas reservoirs were available. Perhaps mergers contributed. Perhaps early galaxies supplied fuel more effectively than expected. Perhaps multiple factors combined. Researchers continue investigating, because understanding how J0529-4351 formed may help explain how many other supermassive black holes formed as well. Interestingly, black holes don't need to consume stars directly to grow. Popular media often depict stars being swallowed whole. While that certainly can happen, gas is often the preferred meal. Gas is abundant, gas is flexible, gas can lose energy and move inward gradually. Stars are comparatively difficult to capture. They're compact, they're fast-moving, they're less cooperative. Gas behaves more like a fluid reservoir continuously feeding the central engine. J0529-4351 appears to have access to an extraordinary supply, enough to maintain one of the most luminous quasars ever observed, enough to sustain one of the highest known accretion rates, enough to transform a black hole into a beacon visible across much of the observable universe. There's something almost paradoxical about that outcome. Black holes are famous for darkness, yet the hungriest black holes become the brightest. The more aggressively they feed, the more visible they become. The darkness remains hidden behind the event horizon. Meanwhile, the surrounding accretion disk announces its presence across billions of light years. In a sense, J0529-4351 is not famous because of the black hole itself. It's famous because of the spectacular consequences of feeding that black hole. The feast creates the light show, the appetite creates the beacon, the growth creates the record. Now, at first glance, the whole situation seems a little unfair. A black hole is famous for trapping light. Its defining characteristic is that light cannot escape once it crosses the event horizon. So why do some black holes become the brightest objects in the universe? Why does J0529-4351 shine with the power of hundreds of trillions of suns when the object at its centre is literally defined by darkness? The answer turns out to be one of the most remarkable energy-producing processes in all of nature. And strangely enough, the light isn't generated by what happens after matter falls into the black hole. The light comes from what happens just before. Imagine driving toward a massive traffic jam. The cars aren't moving quickly anymore, everything becomes crowded, vehicles bunch together, heat builds. Friction increases, energy is wasted. The closer you get to the centre of the congestion, the more chaotic things become. Now replace the highway with a gigantic disk of gas larger than our solar system. Replace the cars with trillions upon trillions of particles. Replace ordinary traffic speeds with velocities approaching a significant fraction of the speed of light, and place a 17 billion solar mass black hole at the centre. Suddenly we're getting closer to what surrounds J0529-4351. The gas spiralling toward the black hole isn't falling straight inward. That's an important point. Popular illustrations often show matter plunging directly into a black hole, like water disappearing down a sink drain. Reality is more complicated. Nearly everything in space possesses some amount of angular momentum. In simple terms, things are already moving sideways. The Earth doesn't fall directly into the Sun because it's moving around it. The Moon doesn't fall directly into Earth because it's moving around Earth. Likewise, gas approaching a black hole usually has sideways motion. Instead of dropping straight inward, it begins orbiting. The result is an accretion disk, a gigantic rotating structure made of superheated gas. At first, the gas may orbit relatively far from the black hole, but collisions gradually change things. Individual particles bump into one another. Energy is exchanged. Momentum is redistributed. Some particles move outward, others drift inward. Slowly but relentlessly, matter begins spiraling closer to the event horizon, and that's where the fireworks start. Because gravity near a supermassive black hole is incredibly powerful, every time gas moves inward, it falls deeper into a gravitational well. The process is somewhat similar to a skier descending a mountain. At the top, gravitational potential energy is stored. As the skier descends, that energy converts into motion. The lower they go, the faster they travel. Gas falling toward J0529-4351 undergoes the same basic transformation. Gravitational energy becomes kinetic energy. The closer the gas gets to the black hole, the faster it moves. Much faster. Near the inner regions of the accretion disk, material can travel at astonishing speeds. Not hundreds of kilometers per hour, not thousands, not even millions. We're talking about significant fractions of light speed. The fastest moving gas races around the black hole at velocities difficult for the human mind to appreciate. Imagine travelling around Earth several times every second. Even that comparison barely captures what's happening. Particles zip through the disk at extraordinary speeds, and when particles moving that fast collide, something interesting happens. Actually, something very hot happens. The collisions convert motion into thermal energy. Gas temperatures rise dramatically, then they rise further, then further still. Eventually, the disk becomes one of the hottest environments in the known universe. To appreciate the scale involved, let's begin with something familiar. The surface of the Sun is roughly 5,500 degrees Celsius. That's hot enough to vaporize virtually anything we encounter on Earth. It's hot enough to sustain nuclear-powered stellar activity. It's hot enough to make standing nearby a thoroughly unpleasant experience. Yet portions of an active quasar's accretion disk can become significantly hotter. Much hotter. Some regions reach temperatures of tens of thousands of degrees. Others climb into hundreds of thousands. Closer to the black hole, temperatures can exceed millions of degrees. At those temperatures, ordinary matter behaves differently. Atoms lose their electrons. Gas transforms into plasma. Radiation pours outward across multiple wavelengths. Visible light, ultraviolet radiation, X-rays. The entire system becomes a gigantic energy factory, and all of it is powered by gravity. That's perhaps the most astonishing aspect. The Sun shines because of nuclear fusion. Hydrogen atoms fuse together. Mass converts into energy. The process powers stars throughout the cosmos, but quasars rely on a different mechanism. They are powered primarily by gravity itself. Matter falling inward releases enormous amounts of energy before ever reaching the event horizon. In fact, black hole accretion can be more efficient than fusion. That statement deserves a moment of attention. For over a century, stars represented nature's benchmark for energy production. Nothing seemed more impressive. Then astronomers discovered quasars. and suddenly the universe revealed an even more powerful engine. Suppose you had a given amount of matter, feed that matter into a star, and some portion of its mass eventually becomes energy through fusion. Feed the same amount into a rapidly growing black hole, and the resulting energy output can be even greater. Nature, it seems, has more than one way of generating extraordinary amounts of power. J0529-4351 happens to be using one of the most effective methods ever observed, and because the black hole consumes roughly 1 solar mass every day, the energy production becomes staggering. Every second, enormous quantities of gravitational energy transform into radiation. Photons stream outward in all directions. Some begin journeys lasting billions of years. A tiny fraction eventually reaches Earth. Those ancient photons are what allowed astronomers to discover the object in the first place. There's another fascinating detail hiding inside this process. The gas surrounding the black hole doesn't glow uniformly. Different regions produce different forms of radiation. The outer disk is relatively cooler. The inner disk becomes much hotter. Still closer to the black hole, temperatures become extreme enough to generate intense ultraviolet and X-ray emissions. It's almost like a cosmic furnace with multiple temperature zones. Except the furnace spans distances larger than planetary systems and generates more energy than entire galaxies. Astronomers study these emissions carefully because they reveal information about the black hole itself. Different wavelengths tell different stories. The brightness reveals feeding rates. Spectral features reveal temperatures. Variations reveal structure. Piece by piece, researchers reconstruct environments they can never directly visit. It's a remarkable achievement when you think about it. Humanity sits on a small rocky planet orbiting an ordinary star. Yet by analysing ancient photons, we can infer the behaviour of gas swirling around a black hole located billions of light years away. The universe doesn't make things easy, but it leaves clues, and astronomers have become exceptionally good at reading them. One of those clues involves the incredible stability of J0529-4351's brightness. You might expect such a violent environment to be chaotic, explosive, unpredictable, yet quasars often maintain extraordinary luminosities for extended periods. The system behaves less like a bomb and more like an engine, a very large engine, a very powerful engine, but still an engine. Fuel enters, energy emerges, the process continues. As long as sufficient gas remains available, the black hole can keep shining. This helps explain why quasars became visible across such immense distances. They're not brief flashes, they're long-term beacons. A supernova might outshine a galaxy temporarily. A quasar can remain luminous for millions of years. That persistence dramatically increases the chances of detection. And when the quasar happens to be as powerful as J0529-4351, visibility becomes almost unavoidable. Even across 12 billion years of travel, the signal remains strong enough for modern telescopes to detect. That's a remarkable statement. Think about how much had to happen for that observation to become possible. The light began its journey when the universe was young. It crossed expanding space. It survived encounters with gas clouds and galaxies. It travelled through cosmic history itself. Eventually it reached Earth, then a telescope, then a detector, then a computer, then the eyes of researchers, all because gas falling toward a black hole generated enough light to remain visible after 12 billion years. The entire process feels almost unbelievable, yet the physics behind it is surprisingly straightforward. Gravity accelerates matter. Matter heats up. Hot matter radiates energy. Energy escapes. The brightness becomes visible across cosmic distances. Of course, straightforward is a relative term when discussing an object capable of consuming the mass of the Sun every day. Even among quasars, J0529-4351 stands apart. Most active black holes simply don't receive enough fuel to sustain such extraordinary luminosities. Many spend long periods dormant, others feed modestly, Only a rare few achieve truly extreme accretion rates, and among those rare systems, J0529-4351 appears to occupy the uppermost tier, a record holder among record holders, a black hole whose appetite transforms gravity into one of the brightest displays in the observable universe. A surprising thing happens whenever people first learn about quasars. They usually start by focusing on the black hole. The black hole is bigger, more famous, more mysterious. It gets the headlines, it gets the documentaries, it gets the dramatic computer animations where stars spiral helplessly toward darkness. But if astronomers are being completely honest, the black hole itself isn't usually the star of the show. The real spectacle is what surrounds it. In fact, if you could somehow travel across billions of light years and approach J0529-4351 safely, the black hole itself would remain invisible. You wouldn't see a giant dark sphere hanging in space. You wouldn't see some cosmic monster floating among the stars. What would grab your attention immediately would be the accretion disk, a vast rotating structure of superheated gas, a furnace powered by gravity, an engine so powerful that it transforms an otherwise invisible black hole into one of the brightest objects in the observable universe. And without that accretion disk, nobody on Earth would know J0529-4351 exists. The black hole would remain hidden, silent, dark, undetectable across such immense distances. Everything we see comes from the disk. Everything. The brightness, the radiation, the energy, the quasar itself. To understand why J0529-4351 is so extraordinary, we need to spend some time exploring this remarkable structure, because in many ways, the accretion disk is the true engine behind the entire phenomenon. Let's begin with a simple question. What exactly is a quasar? The term itself has an interesting history. Back in the 1950s and 1960s, astronomers began discovering strange objects that looked like stars but behaved very differently. Through telescopes, they appeared as tiny points of light. They weren't obviously galaxies. They weren't obviously nebulae. They looked star-like. Yet when scientists examined their spectra, something didn't make sense. The objects appeared unbelievably distant, far more distant than ordinary stars, and if they were truly that far away, they must be producing unimaginable amounts of energy. Initially, many researchers struggled to believe the calculations. The implied luminosities seemed ridiculous. No ordinary star could generate that much power. No known process seemed capable of explaining them. Eventually, however, the evidence became overwhelming. These mysterious objects were real. They became known as quasi-stellar radio sources. Over time, the name was shortened. Quasi-stellar, quasar. Today, we know what they are. A quasar is an actively feeding supermassive black hole surrounded by an accretion disk. That's the short version. The long version is far more fascinating, because a quasar is essentially gravity operating at its most spectacular. Imagine you had an unlimited supply of gas. Now place a gigantic black hole nearby. The gas begins falling inward. But because the gas possesses angular momentum, it doesn't drop directly into the black hole. Instead, it starts orbiting. The material spreads into a disk. The disk rotates. Collisions occur, temperatures rise, energy is released. The entire structure begins glowing. Then it glows more, then more. Eventually, the accretion disk becomes brighter than entire galaxies. At that point, you've created a quasar. The process sounds straightforward. The reality is astonishing, because accretion disks are among the hottest structures known in the universe, and J0529-4351 may possess one of the most extreme examples ever discovered. To appreciate why, imagine standing beside a campfire. The heat feels intense. Move closer and the temperature increases dramatically. Now compare that campfire to a blast furnace. Then compare the blast furnace to the surface of the sun. The sun's surface reaches approximately 5,500 degrees Celsius. Already we have entered a realm completely detached from everyday experience. No human can truly visualize such temperatures, yet even the Sun begins looking modest compared with parts of an active quasar's accretion disk. The outer regions of the disk may measure tens of thousands of degrees, move inward and temperatures climb further, hundreds of thousands of degrees, then millions. The closer gas approaches the black hole, the more extreme conditions become. At these temperatures, matter exists as plasma. Atoms lose electrons. Particles move at extraordinary speeds. Radiation floods outward continuously. The disk effectively becomes a gigantic energy converter. Gravitational energy enters, electromagnetic radiation emerges, and the scale of the conversion is difficult to exaggerate. Suppose someone handed you a kilogram of matter and asked you to produce as much energy as possible. Most methods would struggle. Chemical reactions are relatively inefficient. Even nuclear reactions convert only a fraction of mass into energy. Accretion disks around black holes operate in a different league entirely. Matter spiraling toward a black hole can release astonishing amounts of energy before crossing the event horizon. In some cases, the efficiency exceeds what occurs inside stars. That's one of the great ironies of astronomy. Stars are famous for generating energy. Yet some black holes outperform them, not because the black holes themselves emit light, but because in falling matter becomes extraordinarily hot before disappearing. The process is so effective that quasars became visible across much of the observable universe. Think about that for a moment. The light from J0529-4351 travelled for more than 12 billion years, yet even after crossing such an immense distance it remained detectable. That fact alone tells us something remarkable about the power of the source. Ordinary stars become invisible at much shorter distances. Even entire galaxies can appear faint. Yet J0529-4351 shines brightly enough to attract attention across cosmic history. The accretion disk is responsible for that achievement. In many ways, it functions like a giant lighthouse. A lighthouse doesn't create darkness, it creates visibility. The brighter the beacon, the farther it can be seen. J0529-4351 possesses one of the brightest beacons nature has ever produced. Of course, brightness alone doesn't fully capture what's happening. The disk isn't merely hot, it's dynamic, violent, complex. Imagine a hurricane larger than the solar system. Now imagine every particle inside that hurricane moving at thousands or millions of kilometers per hour. Then imagine temperatures reaching millions of degrees. The result begins approaching the conditions surrounding a powerful quasar. Gas streams collide constantly. Shock waves propagate through the disk. Magnetic fields twist and reconnect. Radiation pushes outward. Gravity pulls inward. Every force seems to participate simultaneously. And somehow the entire structure maintains enough organization to persist for millions of years. That's perhaps one of the most remarkable aspects of quasars. They aren't brief explosions, they're long-term engines. A supernova can briefly rival the brightness of a galaxy, but supernovae fade. Their energy source is finite, their brilliance is temporary. Quasars operate differently. As long as fuel remains available, the engine continues running. Gas enters, energy emerges, the process repeats, month after month, century after century, million year after million year. J0529-4351 appears to have maintained this behaviour for an extraordinary length of time. Otherwise it could never have reached its current mass. The black hole at its centre contains approximately 17 billion solar masses. That enormous mass didn't appear overnight. It accumulated gradually through sustained feeding, and sustained feeding requires a sustained accretion disk, a gigantic reservoir of matter continually supplying fuel. The more researchers study quasars, the more they appreciate how important these disks really are. Without accretion disks, supermassive black holes would remain relatively quiet. Many black holes in the modern universe behave exactly that way. Our own galactic centre provides an excellent example. Sagittarius, a star, contains millions of solar masses. Yet compared with J0529-4351, it appears almost dormant. The Milky Way's central black hole receives relatively little fuel. Consequently, it produces relatively little radiation. The difference isn't necessarily the black hole itself. The difference is the feeding process. Give a black hole enough gas and remarkable things happen. Give it even more gas and you create a quasar. Give it the enormous quantities available to J0529-4351, and you create one of the most energetic objects ever discovered. Interestingly, not all energy escapes as visible light. The accretion disk emits radiation across the electromagnetic spectrum, radio waves, infrared radiation, visible light, ultraviolet radiation, X-rays. Each wavelength reveals different information about the system. Astronomers often describe quasars as multi-wavelength objects because understanding them requires observing many forms of radiation simultaneously. Visible light tells part of the story. X-rays reveal conditions closer to the black hole. Radio observations uncover jets and larger-scale structures. Together, these observations create a more complete picture. It's a little like trying to understand a city. Looking only at daytime photographs tells you something. Looking only at nighttime images tells you something else. Combine every perspective and the city becomes clearer. Quasars work the same way. Every wavelength contributes another clue. J0529-4351 has become especially valuable because its extraordinary brightness provides exceptionally strong signals. The object acts like a cosmic spotlight. Its radiation illuminates not only the quasar itself, but also material located between the quasar and Earth. Gas clouds absorb specific wavelengths. Astronomers analyze those absorption patterns. The result is a surprisingly detailed view of structures located billions of light-years away. In that sense, quasars become scientific tools as well as scientific mysteries. Their brightness allows researchers to investigate otherwise invisible regions of the universe. The brighter the quasar, the more useful it becomes, and few quasars are brighter than J0529-4351. Another fascinating feature emerges near the innermost regions of the accretion disk. Here, gravity becomes so intense that Einstein's theory of general relativity starts playing a major role. Time itself behaves differently. Light paths curve, space becomes distorted. The environment grows increasingly strange. Gas racing around the black hole approaches enormous fractions of light speed. Relativistic effects become significant. The laws governing everyday life continue operating, but under conditions few humans ever imagine. This combination of extreme gravity and extreme temperature creates one of the most exotic environments known to science. Yet despite all this complexity, the basic principle remains surprisingly simple. Matter falls inward. Energy comes out. That's the engine. That's the secret behind quasars. Gravity performs the work. The accretion disk handles the conversion. Radiation escapes into space. The black hole grows. The cycle continues. And in the case of J0529-4351, the process operates on such an immense scale that the resulting luminosity exceeds hundreds of trillions of suns. When researchers first calculated the object's brightness, many were understandably astonished. Not because quasars were unknown. Astronomers have studied quasars for decades, but because J0529-4351 occupies the extreme upper end of the distribution. Every category contains outliers. Every population contains record holders. Every universe apparently contains at least one black hole determined to consume matter at a truly extraordinary pace. That's J0529-4351. A gravitational engine running near the limits nature appears willing to allow. A furnace powered not by combustion or fusion, but by infalling matter. An accretion disk so luminous that it transforms an invisible black hole into a beacon visible across billions of light-years. Several centuries ago, if someone had told an astronomer that future scientists would weigh invisible objects located billions of light-years away, the claim would probably have been met with polite skepticism, or perhaps less polite skepticism. After all, measuring something nearby is difficult enough. Measuring a mountain requires tools. Measuring a planet requires observations. Measuring a star requires mathematics. But measuring a black hole that cannot be seen directly and sits more than 12 billion light-years away? That sounds less like science and more like the beginning of a particularly ambitious fairy tale. Yet that's exactly what modern astronomy does. In fact, one of the most remarkable achievements of contemporary science is the ability to calculate the properties of objects that no human will ever visit, touch, or directly observe. Astronomers routinely estimate temperatures, masses, sizes, motions, and compositions of objects scattered throughout the universe. And somehow, despite the enormous distances involved, the calculations often turn out to be remarkably accurate. J0529-4351 provides a perfect example. Because one of the first questions people naturally ask is this: how do scientists know the black hole contains roughly 17 billion times the mass of the Sun? Nobody can place it on a scale. Nobody can fly a spacecraft there. Nobody can watch it directly. So where does the number come from? The answer begins with light. Almost every major discovery in astronomy ultimately traces back to light. Visible light, radio waves, X-rays, infrared radiation. The universe constantly sends information across space. Astronomers simply learn how to read it. Imagine hearing an ambulance siren. As the vehicle approaches, the sound becomes higher in pitch. As it moves away, the pitch drops. This phenomenon is called the Doppler effect. The same principle applies to light. Objects moving toward us shift their light slightly. Objects moving away shift it differently. Astronomers use these shifts constantly. In fact, much of modern cosmology depends on them. When scientists studied J0529-4351, they examined its spectrum. A spectrum is essentially a breakdown of light into its component wavelengths. Think of sunlight passing through a prism and separating into colours. Astronomers perform a far more sophisticated version of the same process. Each element leaves characteristic fingerprints in the light. Hydrogen produces specific patterns. Helium produces others. Different gases create different signatures. The resulting spectrum becomes a treasure trove of information: temperature, composition, velocity, distance, all hidden within the light itself. For J0529-4351, one crucial clue came from the gas orbiting near the black hole. Remember the accretion disk from our previous discussion? The disk contains enormous amounts of material moving at extraordinary speeds. Some gas circles the black hole at thousands of kilometers per second. Other regions move even faster. When astronomers measure those velocities, they gain an important insight. The faster material orbits, the stronger the gravitational pull must be, and stronger gravity generally means more mass. The logic is surprisingly similar to how we estimate the mass of the Sun. Earth orbits the Sun. The orbital speed tells us something about solar gravity. Solar gravity tells us something about solar mass. The same principle applies around black holes. The only difference is the scale, and the scale is absolutely ridiculous. The gas surrounding J0529-4351 isn't leisurely drifting through space. It's racing around the black hole at speeds that challenge intuition. When astronomers analyze those motions, they realize something extraordinary. Only a truly gigantic object could generate enough gravity to produce such behavior. Then came additional measurements: brightness, luminosity, accretion rates, spectral features. Each independent method pointed toward the same conclusion. The black hole was enormous. Not merely large, not merely supermassive, enormous. Eventually, researchers arrived at an estimate of roughly 17 billion solar masses. At that point, the challenge shifted. The problem was no longer measuring the object. The The problem became understanding what 17 billion solar masses actually means. Numbers of that size quickly become abstract. So let's build some comparisons. We'll begin close to home. At the centre of our galaxy sits Sagittarius A star. Sagittarius A star contains approximately 4 million solar masses. That sounds immense, and it is. Its gravity controls the motions of stars throughout the galactic centre. Entire stellar populations orbit under its influence. Astronomers spent decades tracking stars whipping around an apparently empty point in space before confirming its existence. Sagittarius. A star dominates the central region of the Milky Way, yet compared with J0529-4351, it begins looking surprisingly modest. Let's imagine shrinking both objects down into something easier to visualize. Suppose Sagittarius A star were represented by a basketball. Using the same scale, J0529-4351 would become something much larger. Not another basketball, not a car, not a house. The comparison would quickly become absurd. You would need thousands of Sagittarius A star-sized black holes to match the mass of J0529-4351. The difference is enormous, and that realization leads naturally to another famous comparison. Because whenever astronomers discuss gigantic black holes, one name tends to appear sooner or later: TON 618. For years, TON 618 occupied a special place in astronomy. It became one of the most famous giant black holes ever discovered. Containing tens of billions of solar masses, TON 618 represented the upper frontier of known black hole growth. Whenever science communicators wanted to discuss truly gigantic black holes, TON 618 usually appeared somewhere in the conversation, and understandably so. Its mass is extraordinary. Its luminosity is extraordinary. Its size is extraordinary. Even among supermassive black holes, TON 618 belongs to an elite category. Naturally, comparisons between TON 618 and J0529-4351 emerged almost immediately. Both are among the largest black holes known. Both power incredibly luminous quasars. Both challenge theoretical models. Both reside near the extreme end of what nature appears capable of creating. In terms of mass, they occupy similar territory. The exact rankings depend on measurement uncertainties and ongoing observations. Astronomy rarely provides perfectly neat lists. Nature has a habit of introducing complications. Still, J0529-4351 unquestionably belongs in the same rarefied class as TON 618. The universe contains billions of galaxies, yet only a tiny fraction host black holes approaching this scale. We're discussing genuine cosmic heavyweights, the equivalent of discovering a mountain range among hills, or perhaps discovering an entire continent where you expected an island. The numbers become even stranger when we compare J0529-4351 to stars. Let's begin with our Sun. The Sun dominates the solar system. Its gravity controls planetary orbits. Its energy sustains life on Earth. Its diameter exceeds 1 million kilometers. To human beings, the Sun already feels unimaginably large. Now multiply its mass 17 billion times. Not its brightness, not its size, its mass. The resulting object enters a category where ordinary intuition becomes almost useless. Even the largest stars ever discovered begin looking modest by comparison. Consider R136A1, one of the most massive known stars. Its mass is estimated at roughly 200 suns, an extraordinary figure for a star, a genuine record holder. Yet compared with J0529-4351, even R136A1 barely registers. The difference between 217 billion is so vast that direct comparison becomes almost comical. It's like comparing a grain of sand to a mountain, or perhaps comparing a bicycle to a continent. Eventually, the scale difference overwhelms the analogy itself. Then there are galaxies. This is where things become particularly interesting. People often imagine galaxies as fundamentally larger than black holes, and in terms of physical size, that's absolutely true. Galaxies span tens of thousands or even hundreds of thousands of light years. Black holes occupy much smaller regions, but mass tells a more complicated story. The Milky Way contains roughly 100 billion to several hundred billion stars. Not all stars resemble the Sun, of course. Many are smaller, some are larger. Still, the total stellar mass of a galaxy becomes enormous, and yet black holes like J0529-4351 begin entering a regime where comparisons with galactic structures become meaningful. This is one reason astronomers find such objects so fascinating. They're no longer merely components of galaxies, they're significant players in galactic evolution. Their gravity influences surrounding matter, their radiation affects star formation, their growth reflects the history of entire galactic environments. The black hole becomes part of the story of the galaxy itself. Perhaps the most difficult comparison involves everyday scales. Human beings evolved to understand ordinary objects, trees, animals, buildings, mountains. We never evolved to visualize 17 billion suns. The numbers lie far outside our natural experience. Still, it's fun to try. Suppose every person alive today represented one sun. Earth currently hosts roughly 8 billion humans. You would still need more than twice the entire global population to reach the mass of J0529-4351 measured in solar units. Imagine lining up every human on Earth and assigning each person responsibility for one sun. Even then, you wouldn't have enough. The black hole would still require billions more. Or consider time. If you counted one number every second without sleeping, it would take more than 500 years to reach 17 billion. 500 years, and that's just the number itself, not the mass it represents. The human brain was not designed for these scales. Astronomy regularly forces it to adapt. Yet despite all these comparisons, another question remains. How big is the black hole physically? Mass and size are not the same thing. A black hole's size depends on its event horizon. The more massive the black hole, the larger the event horizon becomes. For J0529-4351, the event horizon spans an astonishing distance, large enough to engulf our entire solar system many times over. Imagine replacing the Sun with the event horizon of J0529-4351. The boundary would extend far beyond planetary orbits. Mercury disappears, Venus disappears, Earth disappears, Mars disappears. Even the outer planets would face serious trouble. The scale becomes genuinely difficult to visualize, and remember, that's merely the event horizon. The surrounding accretion disk extends even farther. The engine powering the quasar occupies an enormous region of space, one of the most energetic structures in the known universe. Yet perhaps the most remarkable aspect isn't the size itself. It's the fact that we know about it at all. Think about what astronomers accomplished. An invisible object, located more than 12 billion light-years away, observed only through ancient photons. And somehow researchers measured its distance, estimated its mass, calculated its feeding rate, and determined its luminosity. That achievement is remarkable in its own right. It speaks to the power of science as a method, not because scientists possess magical abilities, but because nature follows rules. Light behaves predictably, gravity behaves predictably, physics behaves predictably. By studying those rules carefully, humanity can infer astonishing things about places we will never visit. J0529-4351 is a perfect example. We cannot travel there, we cannot touch it, we cannot observe it directly, yet we can learn about it, we can estimate its mass, we can reconstruct its behavior, we can understand its role in cosmic history, and the more we learn, the stranger the object becomes. There's something wonderfully strange about astronomy. Most sciences study things as they are. A biologist can observe a living cell in the present. A chemist can watch a reaction unfold in real time. A geologist can examine a rock exactly where it exists today. Astronomy doesn't always have that luxury. When astronomers look into space, they often aren't seeing the present at all. They're seeing history, sometimes recent history, sometimes ancient history. And in the case of J0529-4351, they're looking astonishingly far into the past. In fact, one of the reasons this object fascinates researchers so much has nothing to do with its brightness or its mass. It's the era from which its light comes, because every photon arriving from J0529-4351 today began its journey more than 12 billion years ago. Think about that for a moment. Not 12 years, not 12,000 years, not 12 million years, 12 billion years! The light entering telescopes tonight started travelling toward Earth long before our planet existed, long before our sun formed, long before the Milky Way reached its modern shape, long before anything resembling human civilization could even be imagined. In a very real sense, J0529-4351 is a message from a different cosmic age, and that's what makes this section of our journey particularly fascinating, because we're about to explore one of the strangest facts in all of astronomy. Looking far away means looking backward in time. At first, this sounds impossible. Time travel belongs in science fiction. Astronomers don't own time machines. Observatories aren't equipped with buttons labelled "Travel to the Early Universe." Yet the effect is completely real, and it happens because of something deceptively simple. Light takes time to travel. That's it. That's the secret. The speed of light is incredibly fast, approximately 300,000 kilometers every second. Every second. The number is so large that light could circle Earth more than 7 times in a single second. From a human perspective, that's practically instantaneous. Flip a light switch and the room illuminates immediately. Look at the moon and it appears present. Look at the sun and it feels present. Our everyday experience creates the illusion that light arrives instantly. But space is so large that even light struggles to cross it quickly. Consider the sun. Sunlight reaching your face right now did not leave the sun right now. It left approximately 8 minutes ago. The sun you see is always 8 minutes in the past. Fortunately, that's not usually a problem. 8 minutes isn't particularly dramatic. If the sun vanished, which thankfully it won't, Earth wouldn't know for 8 minutes. Then we'd have larger concerns. Now let's move farther outward. The nearest star system beyond the sun is approximately 4 light years away. That means its light requires 4 years to reach us. Tonight we're seeing those stars as they existed 4 years ago. Not now. 4 years ago. Again, not too dramatic. But the principle has already appeared. Distance creates a time delay. The farther away something is, the older the image becomes. Let's keep moving. The beautiful spiral galaxy known as Andromeda Galaxy sits approximately 2.5 million light-years away. When you look at Andromeda, you're seeing light that began its journey roughly 2.5 million years ago. At that time, early human ancestors still walked across Earth. Modern civilization didn't exist. Agriculture didn't exist. Writing didn't exist. The light started travelling before any human ever built a city. Yet compared with J0529-4351, Andromeda is practically next door. The quasar resides at an entirely different scale. Its light has been travelling for more than 12 billion years, and that fact places it among the most valuable objects astronomers can study. Because the farther we look, the younger the universe becomes. Imagine owning a collection of family photographs. The most recent photographs show people as they are today. Older photographs reveal earlier periods, childhood, teenage years, parents as young adults. Grandparents decades before you were born. The farther back you go, the younger everyone appears. Astronomy works similarly. Nearby objects reveal the modern universe. More distant objects reveal earlier periods. Extremely distant objects reveal the universe during its youth. J0529-4351 belongs firmly in that last category. We're seeing it during an era when the universe was only a fraction of its current age. Today the universe is approximately 13.8 billion years old. When the light from J0529-4351 began travelling toward Earth, the universe was dramatically younger. Galaxies were still evolving. Stars were forming at enormous rates. Cosmic structures were still assembling. Many familiar features of the modern universe had not yet fully developed. It's difficult to overstate how valuable this perspective is. Human beings cannot observe cosmic evolution directly. The process takes billions of years. No astronomer can watch a galaxy evolve from birth to maturity. The timescales are simply too large. Instead, astronomers study different galaxies at different distances, some nearby, some intermediate, some extremely distant. Together, these observations create a timeline, like examining photographs from different stages of a person's life. J0529-4351 occupies one of the earliest positions on that timeline, and that's where things become especially interesting, because the object shouldn't really exist quite the way it does, or at least not according to some of the simplest models. Remember the black hole at the centre of J0529-4351, approximately 17 billion solar masses, one of the largest known black holes, one of the most actively feeding, one of the brightest quasars ever discovered. Now combine that information with the object's age. We're observing it when the universe was still relatively young. Suddenly a mystery appears. How did such an enormous black hole grow so quickly? This question keeps astronomers awake at night. Well, perhaps not literally. Astronomers tend to have many reasons for staying awake, but it certainly occupies a great deal of scientific attention, because black holes don't begin life as 17 billion solar mass giants. They grow, they accumulate matter, they merge, they evolve. All of those processes require time, yet J0529-4351 appears astonishingly mature for the cosmic era in which we observe it. It's a little like discovering a fully grown forest in a landscape that was planted only recently. Something about the growth process seems surprisingly efficient. Either the black hole started growing extraordinarily early, or it consumed matter extraordinarily fast, or some combination of both. Researchers continue investigating these possibilities, and every new observation provides additional clues. One reason quasars are so useful is that they act as cosmic lighthouses. Their tremendous brightness allows astronomers to study the early universe in remarkable detail. Imagine standing on a dark coastline. Far offshore, a powerful lighthouse shines through the night. Even if you cannot see the surrounding landscape, the lighthouse reveals information about the environment between you and it. Mist becomes visible, clouds become visible, rain becomes visible. The light exposes structures that would otherwise remain hidden. Quasars perform a similar function on cosmic scales. The light from J0529-4351 passes through enormous regions of space before reaching Earth. Along the way, it encounters gas clouds, intergalactic material, proto-galaxies, various structures scattered throughout the universe. Some wavelengths are absorbed, others continue onward. The resulting patterns become scientific clues. Astronomers analyze those clues to learn about regions that would otherwise remain invisible. In some cases, the quasar itself becomes almost secondary. The light acts as a probe, a tool for studying the universe through which it travelled. That's one reason researchers become excited whenever a particularly bright quasar is discovered. Brighter quasars produce stronger signals. Stronger signals reveal more information, and few signals are stronger than those from J0529-4351. Another fascinating aspect of looking backward in time involves the expansion of the universe. When the light left J0529-4351, the universe was smaller than it is today. not dramatically smaller in everyday terms, but significantly smaller on cosmic scales. Over billions of years, space itself expanded. Galaxies moved farther apart. Distances increased. The universe continued growing. This expansion affects the light itself. As space stretches, wavelengths stretch too. Astronomers call this phenomenon redshift. It's one of the most important concepts in cosmology. Imagine drawing a series of evenly spaced dots on a rubber band. Now stretch the rubber band. The dots move farther apart. Light behaves similarly. As the universe expands, wavelengths become stretched. Blue light shifts toward red. Ultraviolet light shifts into visible wavelengths. Visible light shifts into infrared. The greater the distance, the greater the stretching. By measuring redshift, astronomers estimate how far away an object is and how long its light has been travelling. J0529-4351 exhibits an enormous redshift. One of the signatures of its extraordinary distance. Without redshift measurements, modern cosmology would be almost impossible. It's one of the primary tools allowing scientists to reconstruct cosmic history, and it transforms every distant observation into a glimpse of the past. The effect can feel almost unsettling when you think about it carefully. Tonight, somewhere in the universe, J0529-4351 may look completely different. The quasar we're observing existed billions of years ago. Its current state remains unknown. Perhaps it continues shining. Perhaps it has changed dramatically. Perhaps the feeding rate has slowed. Perhaps the surrounding galaxy evolved substantially. We don't know. The information hasn't reached us yet. In fact, it won't reach us for billions of years. We're permanently observing an earlier version of the object, a younger version, a historical version. Astronomy constantly reminds us that now is a surprisingly local concept. Across cosmic distances, every observation becomes a time capsule. Every galaxy becomes an archive. Every quasar becomes a historical document. And J0529-4351 happens to be one of the brightest historical documents ever discovered. There is something deeply humbling about that realization. The photons entering telescopes tonight began their journey before Earth existed. They travelled through the formation of our solar system. They travelled through the rise of dinosaurs. They travelled through mass extinctions. They travelled through the evolution of mammals. They travelled through the appearance of humanity. They travelled through every civilization ever built. Only now are they arriving, a 12 billion year journey ending in a telescope mirror. And thanks to that journey, we gain a glimpse of a younger universe, a universe still assembling its largest structures, a universe already capable of producing black holes so enormous that modern astronomers continue struggling to explain them. Let's imagine, just for a moment, that technology has advanced so far into the future that humanity can travel almost anywhere, not next year, not next century, perhaps millions of years from now. Civilizations rise and fall, stars continue orbiting the Milky Way, entire continents drift across Earth's surface, technology advances beyond anything we can currently imagine. Eventually someone decides to visit J0529-4351. It sounds exciting at first. After all, who wouldn't want to see the brightest known quasar up close, the most powerful black hole ever discovered? One of the greatest engines in the universe, a cosmic lighthouse visible across billions of light years. But the closer you examine the idea, the more obvious it becomes that J0529-4351 is one of the most hostile places imaginable. In fact, calling it hostile might be understating the situation. A lava field is hostile. The surface of Venus is hostile. The centre of a hurricane is hostile. J0529-4351 belongs to an entirely different category. It's the sort of place where multiple laws of physics simultaneously decide that your continued existence is no longer a priority. And that's before you've even reached the black hole itself. The first problem would be the radiation. Whenever people imagine dangerous black holes, they usually think about gravity. They picture being pulled inward, stretched apart, dragged toward the event horizon. Gravity certainly becomes important eventually, but long before gravity becomes your biggest concern, radiation would likely end the journey. Remember the accretion disk surrounding J0529-4351. That enormous rotating structure isn't merely bright, it's unimaginably bright. The disk emits visible light, ultraviolet radiation, X-rays, and other energetic forms of electromagnetic radiation. The output exceeds hundreds of trillions of suns. To appreciate what that means, consider Earth's relationship with our own sun. We sit approximately 150 million kilometers away. That distance is extremely important. Move significantly closer and temperatures rise dramatically. Move significantly farther away, and Earth becomes increasingly cold. Life exists partly because we're positioned within a relatively favourable range. Now imagine replacing the Sun with the quasar J0529-4351, not the black hole itself, the entire active quasar, the accretion disk, the radiation, the enormous energy output. Suddenly Earth's current orbit would become completely unsuitable. In fact, unsuitable is being polite. The planet would be sterilized almost immediately. Oceans would not merely evaporate. Atmospheric chemistry would break down. Surface temperatures would climb to extraordinary levels. Complex life would disappear. The environment would become utterly transformed. And that's the distance we currently consider close to the Sun. J0529-4351 produces so much energy that safe distances become difficult to imagine. Even entire planetary systems would struggle to remain habitable nearby. This leads to an interesting realization. People often think of black holes as dark threats hiding in space. J0529-4351 is the opposite. Its danger comes largely from its brightness. The quasar shines so intensely that radiation becomes one of the primary hazards. In a strange way, the most dangerous aspect of the black hole isn't the darkness, it's the light. Suppose our hypothetical future spacecraft somehow survives this problem. Advanced shielding, exotic technology, remarkable engineering. The crew continues approaching. Now another challenge emerges. The environment surrounding the quasar is far from calm. Gas clouds move at extraordinary speeds. Magnetic fields twist through space. Shock waves propagate through the surrounding material. Particles accelerate to tremendous energies. The region resembles a gigantic cosmic storm, not a weather system, a plasma system, a gravitational system, an electromagnetic system, all operating simultaneously. Imagine attempting to fly through the center of a hurricane while also navigating a volcanic eruption and a lightning storm. Then increase the scale by several orders of magnitude. The comparison still falls short. Near J0529-4351, enormous quantities of matter continuously move through the accretion disk. Material collides, heats up, accelerates, radiates energy. The environment remains dynamic and violent, not the sort of place one would choose for a peaceful vacation. Even if a spacecraft could somehow tolerate the radiation and turbulence, another problem awaits: heat, and not ordinary heat. The temperatures near portions of the accretion disk reach extraordinary levels, millions of degrees in some regions, far hotter than stellar surfaces, far hotter than anything humans have ever encountered directly. Of course, space itself remains mostly empty. You don't automatically absorb all that heat merely by being nearby. But the radiation generated by those temperatures becomes a serious issue. It's one thing to observe a furnace. It's another thing entirely to sit beside one producing the energy output of hundreds of trillions of suns. The closer our imaginary travellers move toward the disk, the more difficult survival becomes. Then comes gravity. This is the danger most people expect, and for good reason. The black hole at the centre of J0529-4351 contains approximately 17 billion solar masses. That's an extraordinary amount of mass concentrated into a relatively compact region. Its gravitational influence extends enormous distances. Stars, gas clouds, dust, entire structures respond to its presence. Yet here's something surprising. If you remain far enough away, gravity itself isn't necessarily the immediate problem. In fact, because the black hole is so massive, the event horizon becomes correspondingly large, and that creates an interesting effect. Near smaller black holes, gravitational differences can become lethal relatively quickly. The pull on your feet becomes much stronger than the pull on your head. The resulting stretching is known as spaghettification, a term scientists somehow managed to make official. Near extremely massive black holes, however, the situation changes. The event horizon expands. The gravitational gradient becomes less severe at the boundary itself. Counterintuitively, a larger black hole can be gentler than a smaller one, at least initially. This sounds reassuring, until you remember that eventually every path still leads inward. Cross the event horizon and escape becomes impossible. Not difficult, not unlikely, impossible. That's what makes black holes unique. Every future direction points toward the center. Every possible trajectory leads deeper into the gravitational well. The universe effectively runs out of exits. If our hypothetical spacecraft crossed the event horizon of J0529-4351, the crew might not notice anything dramatic at first. No wall, no barrier, no sudden impact. The event horizon isn't a physical surface. It's a boundary in space-time. The crossing itself might feel surprisingly uneventful. The consequences, however, become unavoidable. Eventually tidal forces increase, conditions worsen, the inward journey continues, and no information returns. From the perspective of outside observers, the spacecraft simply disappears. Forever. Interestingly, though, the event horizon may not be the most dangerous location near J0529-4351. That title arguably belongs to the accretion disk itself, because unlike the black hole, the disk is visible, the disk is energetic, the disk is violent, the disk is actively converting enormous amounts of gravitational energy into radiation. Flying directly into the accretion disk would resemble flying into a gigantic rotating furnace. A furnace larger than the solar system. A furnace heated by one of the most powerful gravitational engines in existence. Temperatures become catastrophic. Radiation becomes overwhelming. Particles move at extraordinary speeds. Survival prospects decline rapidly. The situation becomes so extreme that even many naturally occurring objects struggle there. Planets, for example, would have a difficult time existing close to an active quasar. Any nearby world would experience extraordinary radiation exposure. Atmospheres could be stripped away. Surface conditions could become hostile. Complex chemistry could be disrupted. The entire environment would differ dramatically from what we associate with habitability. Does that mean life is completely impossible near quasars? That's a more complicated question. Astronomers have learned repeatedly that nature enjoys surprising us. Life exists in deep oceans, inside rocks, near hydrothermal vents, in environments once considered impossible. As a result, scientists generally avoid declaring anything absolutely impossible. Still, the immediate surroundings of J0529-4351 appear extraordinarily challenging. The combination of intense radiation, powerful gravity, high-energy particles and dynamic gas flows creates one of the harshest known environments in the cosmos. If life exists there, it would likely be unlike anything we currently understand. There's another fascinating aspect worth considering. Suppose an advanced civilization somehow developed near J0529-4351. What would their night sky look like? The answer is remarkable. Depending on their location, the quasar could dominate the heavens. Imagine a celestial object vastly brighter than any star. a persistent beacon flooding the sky with energy, a cosmic centerpiece impossible to ignore. For such observers, the quasar might influence culture, mythology, science, and daily life. Its presence would shape everything. Of course, this remains speculation. We have no evidence of civilizations near J0529-4351. But the thought experiment helps illustrate just how extraordinary the object really is. Most black holes remain hidden. J0529-4351 announces itself across billions of light years. It's not merely present, it's impossible to overlook, and that's perhaps the most important lesson from this entire discussion. The black hole itself may be dark, completely dark, utterly invisible, yet the environment surrounding it becomes one of the brightest and most energetic regions in the known universe. A place where gravity transforms matter into radiation with astonishing efficiency. A place where temperatures reach extraordinary levels. A place where survival becomes increasingly difficult. A place unlike almost anything else humanity has ever discovered. For most of the 20th century, astronomers tended to think of galaxies and black holes as separate stories. Galaxies were galaxies. Black holes were black holes. One occupied enormous stretches of space filled with stars, gas, and dust. The other represented a compact region of intense gravity hidden somewhere near the centre. The assumption seemed reasonable. After all, a galaxy might contain hundreds of billions of stars spread across tens of thousands of light years. A black hole, even a large one, occupied a comparatively tiny region. Surely the galaxy was the main event. The black hole was simply another object living inside it. As it turns out, nature had a more interesting plan. Over the past few decades, astronomers have uncovered evidence suggesting that black holes and galaxies are deeply connected. Not casually connected, not loosely associated, connected in ways that continue surprising researchers today. And nowhere does that relationship become more fascinating than when we examine monsters like J0529-4351. Because the existence of such an enormous black hole raises a profound question. Did the galaxy create the black hole? Or did the black hole help create the galaxy? The answer may be both. Let's begin with something familiar. The Milky Way contains somewhere between 100 billion and several hundred billion stars. It's an enormous structure. Its disk stretches roughly 100,000 light-years across. Stars orbit its centre. Gas clouds drift through its spiral arms. New stars continue forming while older stars gradually die. For a long time, astronomers viewed the galaxy as the dominant feature. The central black hole, Sagittarius A star, seemed comparatively small, important perhaps, but hardly the main architect of galactic evolution. Then researchers began measuring black holes in other galaxies, and a strange pattern emerged. Larger galaxies tended to host larger central black holes. Smaller galaxies tended to host smaller black holes. The relationship appeared again, and again, and again. At first, this seemed like a coincidence. Astronomy is full of coincidences that later disappear under closer scrutiny. But this one refused to go away. As observations improved, the correlation became increasingly convincing. The mass of a galaxy's central black hole often appeared linked to properties of the galaxy itself, not perfectly. Nature rarely offers perfect relationships, but strongly enough to attract serious attention. The implication was remarkable. Somehow galaxies and black holes were influencing each other's growth. This was unexpected. After all, the black hole occupies a tiny fraction of the galaxy's total volume. Imagine a city stretching across hundreds of square kilometers. Now place a single office building near the center. You wouldn't expect that building to control the development of the entire city. Yet evidence increasingly suggested that supermassive black holes may influence structures vastly larger than themselves. How could that happen? The answer involves energy, a tremendous amount of energy. When a black hole actively feeds, It doesn't merely consume matter, it releases enormous quantities of radiation. As we have already discussed, the accretion disk surrounding J0529-4351 generates staggering luminosity. That energy doesn't simply disappear, it interacts with the surrounding galaxy. Gas becomes heated, clouds are disturbed, material is pushed outward, star formation can be affected. In some cases, enormous outflows emerge from the galactic center. Astronomers refer to this process as feedback. It's one of the most important concepts in modern galaxy evolution. The basic idea is surprisingly simple. The galaxy feeds the black hole. The black hole responds by releasing energy. That energy influences the galaxy. The cycle continues. It's almost like a conversation, a gravitational conversation conducted across thousands of light years. The galaxy provides fuel. The black hole provides consequences. Together they evolve. To understand why this matters, imagine a galaxy filled with cold gas. Cold gas is important because stars form from it. When gas clouds collapse, new stars are born. More gas generally means more star formation. Now, suppose the central black hole becomes highly active. Matter falls inward. The accretion disk brightens. Radiation floods outward. Powerful winds emerge. Some of the surrounding gas becomes heated. Some may even be expelled from the galaxy's central regions. Suddenly less material remains available for star formation. The black hole effectively regulates future growth. This process appears throughout the universe. In many galaxies, active black holes seem capable of influencing stellar birth rates. The relationship is so significant that modern simulations of galaxy formation must include black hole feedback. Without it, the simulated universe often fails to resemble reality. That's a remarkable conclusion. A century ago, black holes were largely theoretical curiosities. Today, they're considered fundamental components of galactic evolution, and objects like J0529-4351 represent the most extreme examples of this influence. Because if ordinary active black holes affect galaxies, imagine what a quasar producing hundreds of trillions of solar luminosities might accomplish. The energy output becomes enormous. The surrounding galaxy cannot simply ignore it. Everything nearby feels the consequences: gas clouds, star-forming regions, interstellar material. Entire structures may evolve differently because the black hole exists. In a sense, the galaxy and black hole become partners in a shared history. That realization naturally raises another question. Which came first, the galaxy or the black hole? This question remains one of the great mysteries of modern astronomy. For many years, the conventional picture seems straightforward. Galaxies formed first, stars accumulated, gas collected, structures grew. Then black holes emerged and gradually expanded over time. The sequence felt logical. Large galaxies should take time to assemble. Large black holes should take time to grow. Everyone seemed satisfied. Then astronomers began looking deeper into the universe, and deeper and deeper. Eventually they reached objects like J0529-4351. Suddenly the timeline became uncomfortable, because J0529-4351 exists during an era when the universe was still relatively young. Yet the black hole already contains roughly 17 billion solar masses. Somehow it became enormous very quickly, perhaps surprisingly quickly. The simplest growth models struggle to explain such rapid development. This has led some researchers to consider more complicated possibilities. Maybe black holes began forming earlier than expected. Maybe some black holes started from unusually massive seeds. Maybe growth rates occasionally exceeded traditional assumptions. Maybe early galaxies supplied fuel far more efficiently than modern galaxies. The exact answer remains uncertain. But one thing appears increasingly clear. Black holes became important much earlier than astronomers once believed. The early universe may have been filled with rapidly growing giants. J0529-4351 might simply be one of the most spectacular examples we've found so far. There's another reason these objects fascinate researchers. They help illuminate the history of galaxy formation itself. Remember that we observed J0529-4351 more than 12 billion years in the past. We're seeing the system during an earlier stage of cosmic evolution. It's like finding an ancient photograph of a city under construction. The image reveals information that no longer exists in the present. Similarly, distant quasars reveal how galaxies behaved long ago. And the picture emerging from those observations is increasingly complex. The early universe appears surprisingly active. Star formation rates were often higher. Gas reservoirs were larger. Galaxies collided more frequently. Black holes grew rapidly. Everything seems more dynamic, more energetic, more chaotic. In that environment, the relationship between galaxies and black holes may have been especially important. Researchers sometimes describe the early universe as a period of cosmic adolescence. Structures were still growing, still evolving, still finding their long-term identities. J0529-4351 belongs to that era. An era when some black holes apparently grew with extraordinary efficiency. An era when galaxies and black holes were shaping one another simultaneously. One particularly fascinating idea suggests that black holes may actually help organize galactic development. Not intentionally, of course. Nature rarely operates with intentions, but through feedback mechanisms, black holes may regulate the availability of gas. Regulating gas affects star formation. Star formation affects galaxy evolution. The chain of influence extends across enormous scales. It's remarkable when you think about it. An object occupying a comparatively small region of space may influence structures spanning tens of thousands of light years. The black hole becomes a kind of gravitational heart, not because it controls everything directly, but because its activity affects the environment around it. The analogy isn't perfect. No analogy ever is. Still, it captures something important. Galaxies and black holes are not isolated entities. They're components of interconnected systems. The growth of one influences the growth of the other. The history of one becomes tied to the history of the other, and J0529-4351 represents one of the most dramatic examples known. A black hole so massive and so luminous that understanding its growth inevitably means understanding its galaxy as well. Yet even after decades of research, major mysteries remain. Astronomers still debate how the first supermassive black holes formed. They still debate how quickly growth can occur. They still debate the precise role of feedback in galactic evolution. Objects like J0529-4351 continue challenging existing theories. Every new observation adds information, every new measurement refines models, and every new discovery reminds us that the universe remains more complicated than expected. Perhaps that's the most exciting aspect of all. Science advances not because every question receives an immediate answer. Science advances because nature keeps presenting puzzles. J0529-4351 is one of those puzzles. A giant black hole observed in the young universe, a quasar brighter than entire galaxies, an object whose existence forces astronomers to reconsider assumptions about growth, evolution, and cosmic history. And that brings us to one of the biggest questions still hanging over the entire story. If black holes and galaxies evolve together, and if J0529-4351 reached such an extraordinary size so early in cosmic history, what exactly allowed it to grow so fast? Far out in the universe, beyond distances that challenge imagination, a giant black hole sits at the centre of J0529-4351, consuming matter at a rate that still surprises astronomers. By now, we've explored its brightness. We've explored its enormous mass. We've explored the ancient era from which its light reaches us. We've explored the relationship between black holes and galaxies. Yet one question continues appearing again and again throughout the entire story. How did it become so large? Because if there's one thing that keeps researchers returning to J0529-4351, it isn't simply the object's size, it's the object's timing. The universe appears to have built this giant remarkably quickly, and that's where the real mystery begins. Imagine visiting a newly planted forest. The trees are young, the landscape is still developing, nothing looks particularly mature. Then, standing in the middle of the forest, you discover a tree taller than every skyscraper on Earth. Not merely larger than the surrounding trees, absurdly larger, so large that it appears to belong to an entirely different age. Your immediate reaction would be obvious. How did that happen? How did one tree grow so quickly while everything around it remained relatively young? Astronomers experience a similar feeling when they study J0529-4351. The universe visible around the quasar belongs to an earlier era of cosmic history. Galaxies were younger, structures were still evolving, many systems were still growing. Yet somehow, at the centre of this distant quasar sits a black hole weighing roughly 17 billion suns, a giant already approaching the upper ranks of known black holes, and it achieved this status astonishingly early. To appreciate why this is puzzling, we need to think about growth. Everything grows through accumulation. Trees accumulate matter, mountains accumulate rock, cities accumulate buildings, black holes accumulate mass. Nothing simply appears fully formed, at least not according to our current understanding of nature. A black hole begins smaller, then it gains mass. Gas falls inward. Stars may occasionally be consumed. Mergers may occur. Gradually the black hole becomes larger. The process seems straightforward. The challenge is speed, because even though black holes can grow continuously, they cannot grow infinitely fast. Nature imposes restrictions. Some are surprisingly strict. One of the most important limitations is something astronomers call the Eddington limit. We've touched on it before, but now it's worth exploring more carefully. Imagine trying to pour water into a bucket. At first, the process is easy. Water enters faster than anything leaves. The bucket fills. Now imagine the bucket begins spraying water outward as it fills. The more water enters, the stronger the spray becomes. Eventually, the outward spray starts interfering with the incoming flow. A balance develops. The bucket can still fill, but not arbitrarily fast. Something similar happens around black holes. As matter falls inward, radiation is produced, lots of radiation. The brighter the accretion disk becomes, the more outward pressure the radiation creates. That pressure pushes against incoming material. In effect, the black hole's own brightness begins limiting how rapidly it can feed. Gravity pulls inward. Radiation pushes outward. A balance emerges. This balance defines the Eddington limit. For decades, astronomers viewed this limit as one of the primary speed controls governing black hole growth. The implications are significant. If growth rates remain near the Eddington limit, then building enormous black holes takes time. Lots of time. Millions of years. Hundreds of millions of years. Sometimes longer, yet J0529-4351 appears to have reached extraordinary mass surprisingly early. This creates tension between theory and observation. Not a contradiction, not an impossibility, but a puzzle, a very interesting puzzle. The universe appears to have built something enormous before many models expected it. And whenever nature does that, astronomers start paying close attention. One possible explanation is that the black hole began with an unusually large seed. The term seed black hole sounds almost adorable. It creates images of tiny black holes planted in cosmic soil waiting to sprout. Reality is slightly less charming. The first black holes likely formed in several different ways. Some emerge from massive stars. Others may have formed through direct collapse of gigantic gas clouds. Still others remain subjects of active research. The crucial point is that starting size matters. Suppose two people begin climbing a mountain. One starts at sea level, the other begins halfway up. Even if both climb at the same speed, the second person reaches the summit first. Black holes behave similarly. A larger starting mass requires less subsequent growth. Some researchers suspect that giant quasars may descend from unusually massive seeds. Instead of beginning as ordinary stellar remnants, perhaps they started much larger. If true, the growth problem becomes easier. Not solved entirely, but easier. Another possibility involves sustained feeding. Remember the appetite of J0529-4351. Approximately 1 solar mass every day. That's an extraordinary feeding rate. Ordinary. Yet what if conditions in the early universe made such feeding more common? The young cosmos differed significantly from today's universe. Galaxies contained abundant gas. Collisions occurred more frequently. Material moved through galactic environments differently. In some regions, black holes may have enjoyed access to enormous reservoirs of fuel. Imagine opening a restaurant beside an endless river of customers. Growth becomes much easier. The same principle applies to black holes. Given enough fuel, growth can proceed remarkably quickly. J0529-4351 may represent an extreme example of this process. Perhaps the black hole simply never experienced a shortage of food. Perhaps for hundreds of millions of years, gas continued flowing inward, day after day, century after century, million year after million year. The engine remained active. The mass continued increasing. The giant kept growing. There's also the possibility that black holes occasionally exceed traditional growth expectations. Astronomers continue debating this topic. Some observations suggest that under special conditions, black holes might temporarily feed above the Eddington limit. Not dramatically above, not infinitely above, but enough to matter. Even modest increases sustained over long periods can produce substantial differences. The mathematics of exponential growth can be surprisingly powerful. A small advantage maintained consistently eventually becomes enormous. Think about compound interest. A tiny increase repeated year after year eventually creates dramatic results. Black hole growth can behave similarly. Small differences accumulate. Millions of years pass. The consequences become substantial. Yet perhaps the most fascinating possibility involves mergers. Galaxies collide throughout cosmic history. In fact, the Milky Way itself will eventually merge with the Andromeda Galaxy. When galaxies merge, their central black holes may eventually merge as well. The resulting object becomes larger, sometimes much larger. Imagine two growing companies combining into a single organization. The new entity inherits the assets of both. Black hole mergers operate on a similar principle. Mass combines. The giant becomes larger. Throughout cosmic history, repeated mergers may have contributed significantly to the growth of supermassive black holes. J0529-4351 could represent the outcome of numerous such events. Gas accretion, mergers, large seed masses, perhaps all contributed. Nature rarely restricts itself to a single mechanism. Often, multiple processes operate simultaneously. The result becomes greater than any individual contribution. What's particularly interesting is that J0529-4351 forces astronomers to think about limits. Every field eventually encounters this question. How large can something become? How fast can something grow? Where does nature draw the line? For stars, limits exist. Once stars become sufficiently massive, their own radiation begins disrupting further growth. For planets, practical constraints emerge during formation. For galaxies, environmental factors influence development. Black holes seem no different. At some point, we naturally wonder whether a maximum size exists. Can a black hole grow forever? The answer appears to be complicated. In principle, black holes can continue growing as long as matter remains available. Gravity doesn't suddenly stop working. The event horizon doesn't close for business, the black hole remains ready to accept additional mass. Yet practical limitations arise. Fuel availability becomes important, radiation feedback becomes important, galactic environments become important. Every black hole ultimately depends on its surroundings. Even the most powerful gravitational engine cannot consume matter that isn't there. Imagine owning the world's largest furnace but running out of fuel. The furnace may remain capable of operating, but growth stops. Black holes face similar challenges. Eventually nearby gas becomes depleted. Star formation changes the environment. Feedback effects alter fuel supplies. The easy growth phase ends. This may explain why truly gigantic black holes remain relatively rare. The universe contains billions of galaxies, yet only a small fraction host objects approaching the scale of J0529-4351 or TO618. Creating giants appears possible. Creating them consistently appears much harder. Another intriguing question involves the future. Suppose J0529-4351 continued feeding for billions of years. How large might it become? The honest answer is that nobody knows with certainty. Its environment would evolve, fuel supplies would change, galactic interactions would occur, growth rates would fluctuate. The future depends on many variables. What we do know is that the object already occupies an extreme position. It's not merely large. It's among the largest known. The fact that astronomers can even ask whether larger examples exist demonstrates how extraordinary modern discoveries have become. A century ago, supermassive black holes were speculative ideas. Today, researchers debate the upper limits of objects containing tens of billions of solar masses. Science advances quickly when the universe provides enough surprises, and J0529-4351 certainly qualifies as a surprise. In some ways, its existence represents a challenge issued by nature. Here is a black hole 17 billion times more massive than the Sun. Here is a quasar brighter than entire galaxies. Here is an object observed when the universe was still relatively young. Explain it. Understand it. Build a model that accounts for it. Astronomers have been working on that challenge ever since. Progress continues. Observations improve. Simulations become more sophisticated. The picture grows clearer, yet mysteries remain. And those mysteries are often the most valuable part of science. After all, if every question already had an answer, discovery would be impossible. J0529-4351 reminds us that the universe still contains puzzles. Big puzzles. 17 billion solar mass puzzles. And perhaps the most exciting possibility is that this giant may not be the final record holder. Somewhere beyond the reach of current surveys, even larger black holes may exist. Perhaps brighter quasars remain undiscovered. Perhaps future telescopes will reveal giants dwarfing even J0529-4351. The universe has surprised astronomers before. It will almost certainly do so again, which naturally leads us toward another fascinating question. If objects like J0529-4351 challenge our understanding of cosmic limits, could even larger black holes be waiting somewhere in the darkness, hidden among the countless galaxies we have yet to explore? If there's one lesson astronomy has taught repeatedly over the past century, it's this. Never assume you've found the biggest anything, the biggest star, the biggest galaxy, the biggest explosion, the biggest black hole. History suggests that the universe enjoys making those claims look temporary. Again and again, astronomers discover an object that appears impossibly large. Researchers publish papers, science communicators create documentaries. Everyone becomes comfortable with the new record holder. Then a few years later, a telescope finds something even more extreme. The cycle repeats. That's one reason many astronomers hesitate to use words like ultimate or largest possible. Nature has a habit of challenging certainty. And when we look at J0529-4351, one of the most obvious questions becomes impossible to ignore. Could something even bigger exist? Not slightly bigger, not marginally brighter. Something truly larger. A black hole exceeding 17 billion solar masses. A quasar more luminous than anything currently known. A gravitational giant dwarfing even J0529-4351. At first glance, the idea sounds unlikely. After all, we're already discussing one of the largest and most energetic black holes ever discovered. The object consumes roughly a solar mass every day. Its luminosity rivals entire galaxies. Its mass places it among the elite giants of the cosmos. Surely we were approaching the upper limits, right? Perhaps. But astronomy has taught us to be careful with assumptions like that. Because there's an important distinction between the largest black hole we know about and the largest black hole that actually exists. Those are not the same thing. Not even close. To understand why, imagine standing on a beach and collecting seashells. After several hours, you discover the largest shell you've seen all day. You might reasonably call it the largest shell you've found. But that doesn't mean it's the largest shell on Earth. It only means it's the largest example you've encountered so far. Astronomers face a similar challenge. The observable universe contains hundreds of billions of galaxies, possibly more. Each galaxy may contain a central black hole. Many remain unstudied, some are too distant, others are hidden behind dust. Some simply haven't been observed carefully yet. The universe is an enormous place. Humanity has explored only a tiny fraction of it in detail. As a result, every record holder comes with an important disclaimer. Largest known, brightest known, most massive known. Those final words matter. Known. Because unknown objects may still be waiting. History provides numerous examples. There was a time when the Milky Way appeared to be the entire universe. Then astronomers discovered other galaxies. There was a time when supermassive black holes seemed impossible. Then evidence accumulated. There was a time when quasars appeared completely mysterious. Now we understand their basic nature. Every generation of observations expands the cosmic inventory. Every generation discovers something unexpected. There is no reason to assume that process has ended. In fact, many researchers expect future telescopes to reveal even larger black holes. The real question isn't whether bigger objects are possible. The real question is how much bigger they can become. That brings us back to growth. Black holes grow by acquiring mass. Gas falls inward. Stars occasionally contribute. Galaxies merge. Black holes merge. Over immense spans of time, the mass increases. Theoretically, this process can continue for billions of years. In principle, a black hole doesn't care whether it contains 10 solar masses or 10 billion. Gravity continues operating. Matter continues falling inward. Growth continues. The difficulty lies in maintaining the fuel supply. Imagine trying to build the world's largest city. The challenge isn't constructing a few buildings. The challenge is obtaining enough resources to keep expanding. Eventually you need more land, more materials, more energy, more infrastructure. Growth becomes increasingly difficult. Black holes face similar constraints. The larger they become, the more matter they require to continue rapid growth. And matter isn't distributed evenly throughout the universe. Some environments provide abundant fuel, others do not. This may explain why truly gigantic black holes remain relatively rare. Nature can build them, but creating one requires special conditions. The galaxy must supply enormous quantities of gas. The feeding process must remain efficient. Growth must continue for long periods. Multiple favourable circumstances must align. J0529-4351 appears to have won the cosmic lottery in this regard. Its environment allowed extraordinary growth, yet even among giant black holes, there are other contenders. One of the most famous is TON 618. For years, TON 618 has occupied a near-legendary position in astronomy. Its estimated mass reaches tens of billions of solar masses. Depending on measurement techniques and uncertainties, it remains one of the largest black holes ever identified. When astronomers discuss the upper frontier of black hole growth, TON 618 inevitably enters the conversation. Interestingly, the existence of both TON 618 and J0529-4351 suggests something important. Nature is capable of producing multiple giants. We're not looking at a single freak accident. We're observing a category, a rare category certainly, but a category nonetheless. If the universe can create two such objects, perhaps it can create more, perhaps many more. Another factor worth considering involves time. The universe is approximately 13.8 billion years old. That sounds ancient. And from a human perspective, it certainly is. Yet some processes continue unfolding over billions of years. Galaxies merge, clusters evolve. Structures reorganize themselves. Black holes continue feeding. Given enough time, even modest growth can produce extraordinary results. Imagine a black hole that spends billions of years accumulating matter, not rapidly, not dramatically, just steadily, year after year, million year after million year. The resulting object could become enormous, perhaps larger than anything currently known. In fact, some theoretical studies suggest that black holes containing hundreds of billions of solar masses might be possible under the right circumstances. Notice the phrase, under the right circumstances. That's important. Theoretical possibility and observational reality are not identical. Physics may permit certain objects, nature may rarely create them, or perhaps create them only in special environments. Still, the possibility remains fascinating. A black hole 100 billion times more massive than the Sun. The number feels almost unreasonable. Yet many astronomical numbers feel unreasonable until observations confirm them. Researchers therefore remain cautious. They neither dismiss the possibility nor assume it automatically exists. Instead, they continue searching. Modern telescopes have become extraordinarily powerful. Every year they discover more distant quasars, more distant galaxies, more unusual black holes. Future observatories will push those capabilities even further. The coming decades may reveal objects currently hidden from view. Some may be more distant than J0529-4351. Some may be more massive. Some may challenge existing theories in entirely unexpected ways. That's one reason astronomy remains so exciting. The universe continually supplies new surprises. Another intriguing possibility involves black holes that no longer shine brightly. Most discussions focus on quasars because quasars are easy to find. They're luminous. They attract attention. They announce their existence across billions of light years. But what about giant black holes that stopped feeding long ago? Such objects might be extremely difficult to detect. Imagine an enormous lighthouse whose lamp has gone dark. The structure still exists. It's just harder to notice. Similarly, a gigantic dormant black hole could remain hidden within a distant galaxy. Without an active accretion disk, much of its visibility disappears. Astronomers must rely on more subtle clues: stellar motions, gravitational effects, indirect measurements. It's entirely possible that some of the largest black holes in the universe are relatively quiet. If so, current surveys may underestimate the true upper limits of black hole growth. The situation becomes even more interesting when we consider the observable universe itself. Remember that the observable universe is not necessarily the entire universe. It's simply the portion whose light has had enough time to reach us since the Big Bang. Beyond that boundary may lie vastly more space, more galaxies, more structures, more black holes. We cannot observe those regions directly. Their light hasn't arrived. But if the universe extends beyond our observational horizon, then the total cosmic inventory could be far larger than anything we currently see. Somewhere beyond our view, objects larger than J0529-4351 may already exist. Perhaps many of them. We simply don't know. And uncertainty is an important part of this discussion. Scientists often become comfortable saying we don't know. In fact, it's one of the strengths of science. Acknowledging uncertainty creates room for discovery. Rather than assuming the current record holder represents an absolute limit, astronomers continue gathering evidence. The data will ultimately decide. There's another reason researchers remain cautious about declaring limits. The history of black hole discoveries repeatedly demonstrates that theoretical expectations can change. When quasars were first identified, many scientists struggled to explain their luminosities. When supermassive black holes became widely accepted, their masses seemed extraordinary. Then larger examples appeared, then larger examples still. Every expansion of the observational frontier tends to reveal something unexpected. J0529-4351 itself is a perfect example. A black hole consuming roughly 1 solar mass per day, a quasar brighter than entire galaxies, an object observed when the universe was still relatively young. Several decades ago, many astronomers would have considered such an object astonishing. Today it exists as a measured reality. The lesson's obvious. Nature often exceeds expectations. That doesn't mean infinitely large black holes exist. Physics almost certainly imposes practical constraints. Fuel supplies are finite, galactic environments vary, feedback mechanisms operate, growth becomes increasingly challenging. Yet the precise location of those limits remains uncertain, and that's exactly why astronomers continue searching. Every newly discovered giant helps refine our understanding. Every measurement improves theoretical models. Every extreme object reveals something about how the universe operates. In some ways, J0529-4351 represents both an answer and a question. It answers the question of whether black holes can become extraordinarily massive. Clearly they can. At the same time, it raises a new question. How much farther can nature go? Could there be a black hole twice as massive? 5 times as massive? 10 times as massive? Somewhere among the countless galaxies scattered throughout the cosmos, the answer may already exist. Waiting patiently, waiting for a future telescope, waiting for a future astronomer, waiting for a future discovery. As we reach the end of our journey with J0529-4351, it's worth remembering just how unlikely this entire story would have sounded not very long ago. A century ago, astronomers didn't know that galaxies beyond the Milky Way existed. They didn't know that black holes were real. They didn't know that quasars existed. They didn't know that giant black holes lived at the centres of galaxies. They certainly didn't know that somewhere in the distant universe, a black hole containing roughly 17 billion times the mass of the Sun would be consuming matter so rapidly that it could outshine entire galaxies. Yet today, that object has a name. J0529-4351. A collection of letters and numbers attached to one of the most extraordinary structures humanity has ever discovered. And perhaps that's where we should begin our final reflection. Not with the black hole itself, not with the accretion disk, not with the staggering numbers, but with the fact that human beings can know about it at all. Because when you step back from the details, the existence of J0529-4351 tells 2 stories simultaneously. One story is about the universe. The other is about us. Let's start with the universe. Throughout this series, we've repeatedly encountered the same idea. Nature is bigger than our intuition, much bigger. Human beings evolved on a relatively small planet orbiting a relatively ordinary star. Our brains developed to understand forests, rivers, mountains, weather, animals, and other everyday experiences. Nothing in our evolutionary history prepared us for 17 billion solar mass black holes. Nothing prepared us for distances measured in billions of light years. Nothing prepared us for objects producing hundreds of trillions of times the Sun's luminosity. And yet the universe contains such things. The cosmos does not seem particularly concerned with what humans find intuitive. Again and again, astronomy reveals structures that exceed our expectations. Larger, older, brighter, more energetic, more distant, J0529-4351 belongs firmly within that tradition. Every major characteristic of the object feels excessive. The mass is excessive, the brightness is excessive, the feeding rate is excessive, even the age of the light feels excessive. Everything about the quasar appears to push toward extremes, and that's important because extremes teach us things. Imagine trying to understand how bridges work. Studying an ordinary bridge teaches valuable lessons. Studying the largest bridge on Earth teaches additional lessons. The extremes reveal where limits begin appearing. They expose weaknesses in assumptions. They test theories under the most demanding conditions. Astronomy works the same way. Objects like J0529-4351 function as natural experiments. The universe builds something extraordinary, and then effectively asks scientists a question. Can your theories explain this? Can your models reproduce it? Can your understanding account for what you're seeing? Sometimes the answer is yes, sometimes the answer is not yet. J0529-4351 continues occupying that fascinating space between understanding and mystery. We know a tremendous amount about it, yet we still don't fully understand how such giants formed so quickly. The object simultaneously represents scientific success and scientific uncertainty. That's one reason researchers find it so valuable. It reminds us that discovery never really ends. Every answer tends to generate new questions. Every solved puzzle reveals another puzzle hiding behind it. And nowhere is that more obvious than in the study of black holes. When black holes first emerged from theoretical physics, they seemed almost impossible. Then astronomers found evidence. Then they found more evidence. Then they photographed shadows. Then they detected mergers through gravitational waves. Then they discovered monsters like J0529-4351. Every step expanded the frontier. Every step transformed speculation into observation. And every step revealed a universe stranger than expected. There's another lesson hidden here as well, one that doesn't always receive enough attention. For all their dramatic reputation, black holes are not separate from the rest of nature. They are products of the same physical laws operating everywhere else. The gravity affecting a falling apple contributes to the same framework that governs supermassive black holes. The atoms in your body follow the same fundamental physics as the gas spiraling around J0529-4351. The light reaching your eyes follows the same principles as the photons leaving distant quasars. This continuity matters, because it means the universe is understandable, not completely understood. Those are different things, but understandable. The cosmos is not random chaos. Patterns exist, rules exist, relationships exist. Human beings have spent centuries uncovering those relationships, and every discovery reinforces a remarkable realization. The same laws operate everywhere, across galaxies, across billions of years, across unimaginable distances. The universe possesses an extraordinary consistency. Without that consistency, J0529-4351 would remain forever mysterious. Instead, scientists can study it, measure it, analyze it, understand at least part of its story. Now let's shift toward the second story, the story about us. Because there's something quietly remarkable about the fact that a species living on a small rocky planet can investigate objects like this at all. Think about what had to happen. Somewhere in the distant universe, a giant black hole began feeding. Matter spiraled inward. Radiation flooded outward. Photons started traveling through space. Then billions of years passed. Entire cosmic eras unfolded. Stars formed and died. Galaxies evolved. The solar system emerged. Earth formed. Life appeared. Life evolved. Dinosaurs came and went. Mammals expanded. Human beings emerged. Civilizations developed. Languages appeared. Mathematics emerged. Science emerged. Telescopes were invented. Technology advanced. And eventually, after all that, some of those ancient photons entered a telescope. A detector recorded them. Researchers analysed them. A discovery occurred. It's difficult not to find something profound in that chain of events. The photons left their source before Earth existed. Yet they arrived at precisely the moment when a technological civilization became capable of interpreting them. Of course, there's no evidence that this timing was intentional. The universe does not appear to schedule discoveries for our convenience. Still, the result remains remarkable. A connection formed between two events separated by billions of years. The quasar emitted light. Humanity received the message. Perhaps that's one reason astronomy resonates so deeply with people. It stretches perspective. Most of daily life occurs on relatively small scales. Work, schedules, appointments, emails, deadlines, traffic, household chores, important things certainly, but local things. Astronomy invites us to step outside those scales temporarily. Not because daily life lacks value, quite the opposite. The contrast helps us appreciate both perspectives simultaneously. J0529-4351 exists billions of light years away. Yet you're hearing about it while sitting in a room somewhere on Earth. Perhaps lying in bed. Perhaps relaxing after a long day. Perhaps listening while gradually drifting towards sleep. The distance between those experiences feels enormous, and yet science creates a bridge, a chain of understanding connecting a human mind to one of the most powerful objects ever discovered. That bridge may be one of humanity's greatest achievements. Not the black hole itself, not the telescope, the understanding, the ability to ask questions about reality and gradually uncover answers, even partial answers, especially partial answers, because science isn't really a collection of facts. Facts matter, certainly, but science is fundamentally a process. A way of exploring the unknown, a method for turning mystery into understanding. J0529-4351 embodies that process beautifully. At first, it was simply a point of light. Then observations accumulated, patterns emerged, measurements improved, the picture became clearer. Today we know it's a quasar. We know it's powered by a giant black hole. We know it's extraordinarily luminous. We know its light travelled for more than 12 billion years. We know its mass rivals the largest known black holes. Every one of those insights represents a victory over ignorance, not a final victory. Science rarely provides final victories, but progress nonetheless. And progress matters, because there are still mysteries waiting. Many mysteries. Perhaps larger black holes exist. Perhaps more extreme quasars remain undiscovered. Perhaps future telescopes will reveal entirely new categories of objects. History suggests that possibility should never be dismissed. Every generation believes it understands the universe reasonably well. Then nature introduces another surprise. J0529-4351 may eventually become one more step in that ongoing story. Future discoveries may exceed it. Future observations may expand our understanding further. That's not a weakness of science. It's one of its strengths. Knowledge grows. The frontier moves. Questions evolve. The journey continues. In some ways, that's the perfect place to leave our story. Not with a conclusion, not with a final answer, but with an open horizon. Because the universe doesn't end with J0529-4351. The cosmos extends far beyond this single quasar. Far beyond any individual galaxy. Far beyond every object humanity has currently observed. Somewhere out there, countless discoveries remain hidden. New mysteries, new giants, new surprises, and perhaps, billions of years from now, some future civilization will look back at our era and smile at how small the universe seemed to us. Just as we smile at earlier generations who once thought the Milky Way contained everything. For tonight, though, perhaps it's enough simply to appreciate what we've already learned. a black hole 17 billion times more massive than the Sun, a quasar brighter than entire galaxies, light that travelled more than 12 billion years before reaching Earth, a reminder that the universe remains vastly larger, stranger, and more fascinating than our everyday experience suggests. And as you settle a little deeper into your pillow, perhaps with the room growing quieter and your thoughts becoming softer, it's worth remembering that somewhere in the darkness above, ancient photons are still crossing intergalactic space. Some began their journey before Earth existed. Some will continue travelling long after we're gone. The universe is patient that way. It has time. And every now and then, a tiny world orbiting an ordinary star learns how to listen. While J0529-4351 continues shining across the cosmos, carrying its story through the darkness, countless other stories remain out there waiting to be found.